Looks like we're live. Hello, everyone, and welcome to yet another recreational programming session with Mr. Zozin. About that, but you didn't expect that shit to happen, so let's make a little bit of an announcement and officially start the stream. Red Circle live on Twitch. And what are we doing today on Twitch at Television website? Today we're doing post-apocalyptic software development. If that makes any sense. So I'm gonna give the link to twitch.tv/turning and I'm gonna ping everyone who's interested in being pinged. And go, the stream has officially started. The stream has officially started. So, hello everyone, welcome. I can see people in the chat. So on the previous stream, we checked this very interesting thing called UXN ecosystem, which is a personal computing stack. And essentially, this is a very small virtual machine with different devices attached to it, right? And essentially, you're writing software for that virtual machine in a special Forth-like language. And so then you compile that, your program written in that language into a ROM that you can distribute around and stuff like that. So, and generally, like I looked around the website and so the software behind all of that has a very interesting philosophy of being, I suppose, offline first and right. So overall, it's very interesting philosophy, and it gives me off these like post-apocalyptic vibes, which I really like, and that's why I call today's stream a post-apocalyptic software development. So I think it's pretty much fitting. We wrote a very simple, like hello world like things in that programming language, and I think the time has come to implement something more substantial, something more complex. And I was thinking that what could be more complex than hello world, a very simple hello world? Probably, a game of life, right? Let's implement a game of life. We know how to put graphics on the screen, right? We know how to do loops and stuff like that, right? So let's just go ahead and ramp up the complexity of our challenges, right? So, and after that, maybe we can ramp up even more. We'll see. So, what's interesting is that the documentation for this entire thing is all over the place and kind of difficult to use and track things. So what I tried to do off screen, I tried to read source code of this entire thing instead, and it worked out better than reading documentation. Honestly, like if you want to learn more about UXN, don't read documentation. Maybe read the first like hello world and stuff like that to get the idea. But if you want to get a deeper understanding and more details, just read the source code. Seriously, just read the source code of the virtual machine itself, of the Varvara system and stuff like that. So it gives you more precise information, because this is what the documentation lacks. It kind of lacks the precision and systematicness. Like as I already said, it's all over the place. So you can find the source code of this thing here. I'm gonna copy paste it in the chat, and for people on YouTube, it's gonna be in the description, of course. Right, and let's go ahead and maybe, I don't know, clone this entire thing. Let's go ahead and clone it. So I'm going to be just doing this. I wonder what would be better. I think it would be better to just use HTTPS protocol. Git clone, and let's go. We're cloning this thing. We are in fact cloning. So it is actually super small, and it has just like a build sh script. Right, so you can just run the build sh and it's going to build the entirety of the thing. It's going to have the emulator and the assembler and everything. And it even starts like a small, like a boot ROM automatically with a simple like small file manager and stuff. It's really cool, right? So you can like walk around, but I don't know how to use the keyboard in here. So what I can say, right? I can just use mouse and I can read things in here, right? So it has a small built-in text. I think I can even, yeah, I can like go full screen, and it like feels like a Temple OS or something. It kind of feels like a Temple OS. Like, I don't know how to use the keyboard. There is some sort of like a shortcuts in here, but I have no idea what is BL. Like, I press BL, it doesn't work, it doesn't do anything. So the whole thing doesn't really explain that well how to use it, right? So the mouse works, which is already great. So the arrows work. but enter doesn't work, so I have no idea how to use this thing, honestly, right? But if I just do something like this, it seems to be working. Right, so that's pretty cool. So and that built all of the necessary binaries that we already had. And so the most interesting thing in here is probably the virtual machine itself. It's UXNC. And it's extremely simple, actually. It's extremely simple. Right, so here are all of the opcodes. And for all of these opcodes, there are different macros that modify the state of the virtual machine, I suppose. So that's what they do. Anyways. So let's go ahead and try to like recreate the hello world again. So to start something with, so it's going to be hello Tal. And I already have a highlighting for this entire thing. I already have a highlighting. So we need to take some devices. To be fair, you still kind of need documentation for at least devices, right? So because I want to be able to do console. So you know what? I'm gonna actually copy paste the hello world from whatever we were doing in the previous stream. So let me actually grab that. So there was my stuff in there. I do remember that quite well. And there we go. So here we basically laid out the, the device thingy, right? So now we have a console, and here we wrote a hello world. So we can do something like that in here. So if I now try to do bin UXN Azam, hello Tal, hello Rom, that seems to be working, and then bin UXN emulator. So we don't really have to use emulator. So as far as I know, we can just do CLI, right? So we can just do CLI, and it's basically an emulator without the event loop and without any of these things. So if I want to just print something on the right on the screen, I can just do that, right? So we can try to do something more complex, right? So here we're just doing the loop. I can of course factor out to something like this, print text. So I think it's jump to R, right? So that's what it is. So essentially when you call to this function, it will put a return address to the return stack, which is going to be 2 bytes, right? And to return out of that, you have to jump to something that is on the return stack, and you also have to use the short mode. You also have to do the short mode. Why there's only one person actually spamming in the chat? So I have to put like a subscriber mode. All right. So let me see. So I'm gonna factor out this entire thing. Right, and there we go. So this is gonna be something like that. So print text, there we go, and that should be basically it. So let me try to just do that. There we go. So what I've noticed is that's quite often something messes with my compilation mode, right? So, and I think this is the UXN Tal mode, but let's not focus on that. I don't think it's that important. All right, so that seems to be working. So we managed to factor out hello world, and we may try to just like repeat that several times. Let me try to put maybe like a 0 on the stack. So we're gonna keep the number at the top of the stack as sort of the counter. Right, so it's going to be 1 byte counter. So we're going to duplicate this entire thing, and I suppose I just want to compare to some value. Let's say that we're going to do 5 iterations in here, right? So we're going to do 5 iterations, and now I need to compare that this thing, while this thing is sort of like less than that 5, we're going to let it fall through and perform 1 single iteration. So let me take a look at the opcodes, right? So maybe I'm gonna even start using the virtual machine in here, like UXNC. So I think there was something like a less than, yeah, there we go. So there's a less than. And how does it even work? Okay, so it's literally T and N, and I'm not even sure what is that. Are they popped out of the stack? So there is this T, which is a capital T, and okay, so it is basically part of the stack. You know what? You know what? I need like a tags file, chat. I need a tags file because I want to be able to actually jump around in that virtual machine. Right. So let me find all of the files from here. Right. So yeah, there we go. So here are all of the files of the source code, and I'm gonna just feed them into e-tags. Right, I'm gonna feed them into e-tags, and that gives me the tags file. So that gives me everything. And so let me see. I'm gonna go back into the virtual machine, and less than I should be able to do the following things. So for example, I'm gonna press on that. It asks for the tags file, and I can jump right here. Right, so set X is basically this shift thingy. I can go inside of shift and basically then go back. I can jump around and figure out things, which is kind of cool, I think, so I still don't understand what is 2 minus 1 in this particular case. It's X and Y, right? So maybe it's something about the offsets, So the T itself, I think it's a variable allocated here on the scope of the function, right? And I suppose it's basically C89, I think it's basically C89 because all the variables are... No, not all of the variables at the beginning of the scope, actually. They are... I mean, at the beginning of the body, so some of them are here. And they're using tabs. Really? You're using tabs? I mean, I don't judge, but I mean... Oof. Anyways, so... I don't judge, but oof. So what do we have in here? So T, we already defined T. So S, you have data plus pointer. Right, it's a data plus pointer, and S, I suppose, is a global variable. So it not necessarily has to be a global variable. It's a stack. S is a stack. So that means T stands for the top of the stack. It stands for the top of the stack, and N, I suppose, is something below the... Yeah, there we go. So here is the where data starts, and here is the pointer. So that's the top. N is something below the top of the... L is even lower. X is even lower. Y is even lower. Z is even lower. That's a very interesting convention, my friend. T, N, L, X, Y, Z. Okay, so yeah, maybe N is equal to next. Yeah, maybe N is equal to next, but what is L? So, I mean, it's fine, we figured it out, so that doesn't mean it's that cryptic. So L is last. Okay, why do we have X after L then? So it's more last than last. So what is X then? Because math moment, yeah, exactly. I think that's because just like, you know, I think the names are kind of semi-arbitrary. I think they are semi-arbitrary. Yeah, it does feel like hallucination, like Twitch GPT. So it's funny how people quite often also hallucinate similar to the language models. Anyway, so, oh yeah, they even explained that, right? So there we go. Oh, these are registers. Huh, that's a very interesting. Yeah, so there's sort of like a register. So top 5 elements on the stack are kind of registers. And, that's pretty cool. So this is also layouting of these things. So when you refer to T2, you're referring to these 2 things. And then, yeah, that's very cool. Like, you see, it's already more productive than reading documentation. Like, chat, I'm fucking telling you. Code is the best documentation. Code is the best documentation. You can't argue with that. It's been proven over and over and over and over again. Because it always explains precisely what it does, and it never gets outdated. It never gets outdated because if it does, it doesn't compile. So it forces you to update this thing. Code is the best documentation. Code is the best documentation. All right. So less than. So, and here we have a top, and here we have a thing below the top. So that means we are comparing, yeah, we're comparing think. Oh, that's actually interesting. So if I do less, I think that means I'm actually doing that incorrectly. If I'm doing less, it's gonna be comparing top. Yeah, so this is gonna be that. This is gonna be that, and this is gonna be that. So it is going to. No, it's gonna be fine. It's gonna be fine though. I'm not really sure about the set 2 minus 1. So you do the shift and aha. It's something about updating consume to aha. Maybe that's what it is, right? So you basically explain the amount of bytes you consume, and that kind of, yeah, huh. But why is it -3? Why is it -3? It has something to do with updating the stack, yeah. That definitely has something to do with updating the stack. Anyway. All right. So I think that means it is correct, and we just gonna do LTH. We're gonna do LTH. So if it is true, we actually have to continue this thing. So I suppose it's gonna be negative. Is there something like gech? Great. So I'm pretty sure there's a greater than, but is there something like greater equal? Greater or equal? Maybe not. So this is not equal. Is there something like not? Maybe there is. Maybe there is. There is nip. The over equal. I don't see that. That's very interesting. So there's some multiplication. Maybe there is an inversion? No. So is there something that inverts the bytes, or maybe... Okay. So... That's bizarre. That's bizarre. There's nothing that also inverts the bytes, so I don't see the inversion. The negative is only not equals, but maybe that's the limitations you have to deal with. Maybe that's the limitations you have to deal with, and that's fine. So we also do XOR in here. So this is the division. This is the division, but okay. So you are XOR with 1. Technically, yeah, I see what you mean. I see what you mean. All right. So we can do XOR then. So less than, so we can do just. Can I just do something like this? F. Funnily enough, yeah. So you are, and if it's greater or equal, we probably wanna basically skip, right? So this is going to be like over, right? So this is going to be like over, and over is going to be located in here. And I'm not even sure if having like a relative label in here is generally a good idea, right? So without the main label. So maybe I have to do something like on reset in here just in case. Right, so, and after that, so I suppose all of that stuff kind of consumes, right, and in here we're gonna just increment, and at the end in here we're gonna maybe jump to again, and I suppose this is how you immediately jump, right? So this is how you immediately jump, and this is basically the thing that we can do in here. Right, so invalid token 0 in console. Invalid token 0 in console, and what? Yeah, so this is what my experiments. Okay, so that seems to be working, and it doesn't really work at all, which is rather weird, honestly. Which is rather weird because So is that the other way around? So if I do GTH, no, it doesn't work either. So LTH, it doesn't work either. So that's not what I wanted actually. So that is bizarre, right? So if it's, yeah, let's put it this way, right? If it's greater, right? Because I'm thinking about this operation in the same order as it would be applied to these things. So if it's greater, I wanna basically be over. So that means it's gonna be okay, right? So it's gonna be okay. So let me double check the you know, the virtual machine. Let me double check the virtual machine GTH. Right, so top, no, it's not the same thing. So we're applying the greater not to the top, but to the thing that is below. That is bizarre, right? So that means we have to do LTH, and that is going to, no, it still doesn't work. It doesn't even perform a single time, and this one also doesn't perform a single, yeah, it does perform a single time. So it is greater. So if this thing is greater, right, and that basically performed 5 times, right? So if you want to do 10 times, it is going to be like that. So, and then, so I want to bring back the new line in here, so we can literally see. It's probably not 10 actually. It's actually 11 because we have that extra thing in there. All right, so that means I want to do this thing, which is not going to perform a single time, and I want to invert it, right? So I want to invert it like so with a XOR, right? So where do we have XOR? So EOR. So this is how we're going to, and it doesn't work. This idea of inverting it like that literally doesn't work, and I have no idea why, right? So why it doesn't work? Because so if you have XOR like 0 and you XOR in it with 1, you get 1. If you have 1 and you XOR in it with 1, you get 0. So that makes sense if I put a truth table in here. So there's something weird that's going on. I don't quite understand. All right, so let me repeat what is going on. So we have 0, we duplicate it, we have 0A, so then we perform LTH, right? So we perform LTH, right, which is literally checking the one that is below with this thing. So that becomes true, right? So that becomes true, which effectively, right, turns it into a 1, I suppose, right? So I suppose it turns it into 1. This is at least what I see, because you assign in 1 to T, right? So that's what you do. And then if it is true, right, if it is, right, then we're doing XOR, which is not entirely. So that means what we have to do in here, I suppose, is just do that to actually invert it, because instead of just doing that, right, so I should have not listened to the chat, right? Should have just like did everything myself. All right, so that is going to probably work. Right, there we go. So that seems to be working, and that, all right, is actually equal to exactly 10. So that seems to be okay. That seems to be okay. So we know how to do the loops. We know how to iterate and everything. So that's pretty cool. Now what we, so reading the virtual machine like directly is way more efficient than reading documentation, right? So it's just like it literally explains you how it works. It literally explains you how it works. Now, if we're gonna be doing the you know, game of life, we need to probably so know the size of the area in which we're do know that, right? So like how big of a size of the array it is. Usually I like to know this kind of information at compile time, right? So I usually like to know it at compile time. So, and as far as I know, there was some macros in the entire thing. There was some macros in the entire thing. So let me see. So if I take a look at some of the examples, where are the examples? I remember projects. Okay. So examples, demos. So there's a move. I wonder if there is any macro. So I know that macros start with dollar, right? So the macros start with the dollar. Let me just grab everything and just look for the dollar. I don't remember if it's okay. So here what we have in here. So here's what we have here. So this is what I'm talking about, right? I want to be able to define things like width and height and everything, right? So I want to be able to do that. And apparently you do that with a dollar. But what exactly the macros do? They're probably literally replaced with this value in here, but we can try to confirm that actually, because we have a source code of the assembler itself in here, right? So here is an assembler, right? So an assembler, what it does, it's actually pretty simple, right? So it opens the file, right? And then it assembles the file. Okay, so when it assembles the file, it copies on reset into the scope, right? So on reset is sort of like a thing that is automatically existing there. So then it scans a word, checks that the word is not bigger. It's kind of funny how the entire project always uses hexadecimal and quite rarely uses decimal. That's what's interesting about this. It's just like primarily hexadecimal. So SLN is basically strlen, right? Nothing particularly special. It's a custom SLN. Does it even use anything from standard library? Okay, so it uses at least input. Right, so then we do the parse, right? And we're just looking at what it is. Do you have the case for the, yeah, there we go. So this is the macro and we're just doing the macro. When you're doing the macro, you just check for the duplicates. Then I don't know what that is. What is that? So while you iterate through this thing, and if it's not alphanumeric, oh, string is hexadecimal. You just check whether this thing is hexadecimal. If it's a hexadecimal and the length is divisible, but okay, that's it's kind of interesting. Ooh, right. So hexadecimal has a. So this is a criteria of a hexadecimal. It's a thing that consists of the hexadecimal digits, and the length of that thing is divisible by 2. That's what it is, apparently. Right, because of each character represents a nibble. Okay, that's probably why, by the way, the mode. So there's a rule 110. That's kind of funny. Yeah, it's a rule. So you also probably have a game of life then, right? So because rule 110 is basically game of life, but one-dimensional. But not really. But I mean, right. So hello. So that's probably why when I do something. Yeah, there we go. Okay. Emacs. So what's funny is that according to that tokenizer, at least for the macros, this should have been recognized as a hexadecimal number, but Emacs didn't recognize it as hexadecimal. It's kind of funny. Maybe it's only for the macros, but yeah, generally. So then what's the next thing we do? So macro name is invalid. It's one of the opcodes, or SMP BRK. BRK is not an opcode, is not one of the opcodes. At least internally, right? Internally, it's not considered to be opcode. Oh, probably because like the usual modes of, you know, short mode, return, keep are not applicable to that thing. That's probably why. So macro limit is exceeded. So then you do macro, and then you, okay, and then you basically iterate through rest of the tokens until you encounter the closing curly, right? So first you encounter the curly, you basically skip it. Then you, you know, go until you encounter, you know, curly thing, and you just basically append the tokens into the macro. You just append the tokens into the macro. All right, so that's pretty cool. And of course, you can't define macros within the macros, right? So there's also like limitation and everything. It's kind of interesting how Okay, so what is M? M is a macro, so let me take a look at the definition of a macro. Yeah, it's funny how there's not a single malloc or free in here. All of the arrays are static and everything has a size limitation. So, which actually simplifies the memory management, which is kind of cool. All right, so it definitely simplifies the, the memory management. Okay, so there you go. I didn't have to read an article about macro system of this language. I just looked at the source code and now I understand how it works. So the macro is basically like a single word that gets replaced with a sequence of tokens, and it's literally what it's written in the source code. Again, source code is the best documentation. Source code is the best documentation. All right, so let me see what we want to have. Right, so we're gonna have width. All right, so this is gonna be the width, and we're gonna define width as what? So I don't even have to do these hashes. I honestly don't really understand what's the point of these hashes. So they're supposed to be sort of like immediate something. We can read it in source code. Like, why am I even asking this kind of question? Let's just freaking read it in the source code. Right, so what's up with that? What's up with that? Okay, so hex literal. So if hex literal plus 1, right, if the thing after that, write lit byte. So you just write a literal byte. Right, if it's bigger, you write short. So is there any difference between something like this and something like this? Is there any difference? We can find that out. Actually, we can find it out. So we know that, so to write a literal byte, this is the function that you use, right? And then let's actually go down where, yeah, there we go. There's literally no difference between them. According to the code, if I understood code correctly, there's literally no difference between writing something like this and something like this. Can your documentation do that? Can you look at the documentation written by a human, right, and tell me this kind of stuff? Well, I mean, if it's literally written in the documentation. But in the code, it is always up to date, right? Because otherwise it's not going to compile, it's not going to work. Code is the best documentation. I'm telling you. I'm freaking telling you. Okay, Gum. There is a difference using the hash rune adds lit opcode preceding by short. Let me see. Do I see that in the source code? Yeah, so there is a lit byte. And if I just look at that, there is no lit byte. Okay, I see. So the question is, what is a lit byte code? All right, so what is a lit? Write lit byte code. So find op byte code. So one of them. So maybe does it have a special meaning in the virtual? Yeah, there is a special meaning in here. So what do we do? So in case of a lit, so we do shift. So we update pointer by 1 and just read something from the documentation, from the RAM. That's very interesting. That's very interesting. That's very interesting. So yeah. All right, so we'll figure it out a little bit later. Anyways, so let me see. I'm closing the chat. Right now, so what do we got? Maybe in this specific case, but to be fair, if I take a look at the rule 110, they're using this thing, right? So they're using this thing, so that means it's probably fine for me to use it here as well. So now. So this is width, and for the width, I don't want to actually exceed 1 byte. So let's say that we're going to have something like 10, right? So this is going to be width, and maybe the height is going to be the same, right? So the height is going to be roughly the same. So when I'm using the width, do I use the width similarly, or do I just like use width directly as a word? Width is not even used anywhere in here throughout the thing. Really cool. Okay, so what is used in here? To mode, do you even use to, okay, so do you even use any of the macros you defined anywhere in here? Wait, why there is so many macros defined in here, none of them used? Okay, this is how you use them. Jesus, bruv, Jesus. But why there is width, but width is never used? It's never used. What's the point of defining it if you never use it? That is bizarre, my friend, that is bizarre. Alright, so, but we're gonna be using it. We're gonna be using it. Anyways. So, I suppose what we want to have is, in fact, an ability to define all these things. Damn, that kind of makes it a little bit difficult to define. For instance, if I want to allocate a board, right? So for instance, I say I have a board and I want to allocate the size of the board. So essentially, if I have 10 by 10, I have to allocate like 100 of them. And by the way, are the things that are in a dollar, are they also hexadecimal? I can always check it out in the assembler. That's what's cool about it, right? So let's actually check it out. So yeah, they are hexadecimal. I can already instantly see that. So, what? That is very interesting. So, if this thing starts with dollar and its hexadecimal is just like a usual padding, but if the next character in the token is ampersand, you can literally put sublabels in there. Huh. That is very interesting. Is that even written in any of the documentations? This is a, this is an Easter egg that the developers don't want you to know. They don't want you to know that, right? So you can only find this documentation in the this kind of stuff in the code. So, thank you so much, Ruby NT, for your subscription. Lit a byte indeed. Lit byte indeed. So what are we going to have? So here's the thing, right? So I want to be able to define width and height, and then I want to be able to say, right, okay, so pad all of that with width and height multiplied together. But I won't be able to do that because this is probably how I have to do that. Right, so there's probably no compile time evaluation, not even like any form of compile time evaluation, right? So there is a way to assign a sequence of tokens to one token and it's gonna get expanded. Because I think that's the entirety of the macros. At least in the source code, I don't see anything else, right? If I take a look at the macro, it's just literally appending the tokens, right? So it's not particularly fancy. So there's a name and there are some items, but this one is interesting actually. So there's it's a two-dimensional array though. It's a two-dimensional one. So that means in the items. I see. It's two-dimensional because it's like a string. Yeah. So it's a array of strings. Right, so array strings. And how much is that, by the way? How much is that? So it's 64. Yeah, not much, right? So essentially it's very much limited, but that's how you're supposed to sort of like train your creativity, right? So you impose limitations on yourself, and that sort of like forces you to come up with more creative solutions. Yeah, that's cool. That's cool. So, and yeah, so that is not going to work. That is definitely not going to work, but I wish it kind of worked. So I wonder if I can do something. Wait a second. I remember there was a calculator. There was a project calculator in there somewhere, and it was all hexadecimal. I think I'm starting to understand why. Because everything in the project is kind of like in hexadecimal, and like it's nice to have a calculator that just helps you with all of that, right? So I can do Uxian emulator, calc-rom, right? So there we go. But I'm not really sure how to use that. So if I want to have like a multiplied by a, and where is equal? I can't see equal. Plus, minus, that. There is no equal. There is no equal. I don't know how to use that. So, yep. Too bad, too bad. They didn't add the equal button, unfortunately. So anyway, what I want you to do, I want you to take 100, which is 10 multiplied by 10, and take a look at the hexadecimal. So this is going to be basically 64, right? So, and the macro system doesn't really allow me to easily do that, so maybe that's why it's not particularly used in that case, but I mean, that's totally fine. So, and essentially, we just pre-allocated the board. I'm not even sure if I had to do this kind of stuff like that, right? So, because maybe I just have all of the memory available to me, like right after the execution. But if I'm going to be adding something afterwards, I think I definitely need to have this sort of thing. So I think that's totally fine. I think that is totally fine. So, interestingly, I remember there in the language there were so-called lambdas. Let me find them. So UXCN design lambdas. It's kind of difficult to find anything in the documentation because it's just a bunch of fractured articles, and sometimes you just want to have like a list of all of them, but it's weird, honestly. Like, it's difficult to find anything. So I'm gonna actually stick to just the source code. But there were lambdas, and as far as I know, lambdas are just curly braces, right? So here they are. So this is a make reference. So let me find the parse. So where is the parse function? So if you have curly, it's not going to start in curly. That's weird. Let me. Okay. So this is in a macro, and this is in a reference. All right. So there is a make reference, and there is a bunch of reference. No, I still need to find that. So there's a syntax. Does it refer to lambda? Okay, so here are the lambdas. Okay, we found it. Right. So the interesting thing about lambdas is that they sort of like define a block of code, right? They sort of define a block of code, and they push the address to that block of code onto the return stack. Right. So they push it onto the return stack. So, which means you can kind of define functions right away. But another interesting thing is that you can jump to that thing, right? So you can define block of code and jump to it. And if you don't jump to it, it will just skip it. So let me see. I think we should be able to even rewrite this entire thing. So if this thing is going to be true, it will fall through. So that means we don't really even have to do something like that, right? We can just check for the condition, right? And if that condition is true, it's gonna fall through, then do the thing, and then it's going to work, hopefully. So let me try to run this entire thing. And no, it didn't work. Do I still need to have the inversion, right? Do I still need to have the inversion? Yeah, I still need to have the inversions. Basically, it calls that thing if it is true. So it's a bit confusing, but that's fine. So that seems to be working. All right. So I would like to maybe make a small break. I would like to maybe make a small break and make a cup of tea. So yeah, let's make a small break, and after I make a cup of tea, we're gonna continue. So we already managed to allocate the board, right? We kind of understand how to do loops. So maybe we can try to print that board, right? Because here is like a one-dimensional loop, but I want to be able to think about that chunk of memory as a two-dimensional thing, right? So I need a way to address like a two-dimensional stuff. So we'll see how we can do that. Okay, so let's go ahead and try to maybe, you know, iterate through all of these things. So we have the board 10 by 10, right? So we have the board 10 by 10. And that raises the question, how can we even do the nested thing, right? How can we do the nested things? So we can think of it this way, right? So I have one sort of iterator, right? I have one iterator. And so I'm checking it like once per iteration, and then I have a second iterator that I also check once per iteration. I can even maybe duplicate it like that, sure. I can quite easily... That's bizarre. What is going on? Is that because of the... Just a second. A tab sneaked in. A tab. I'm trying to start a fight or anything, but this is my code, okay? This is my code. I do whatever I want in my code. You can do whatever you want in your code, okay? You can do whatever you want. So, now, let's do this thing. We have this nested stuff, and that is going to work. So that means effectively we have 2 bytes on top of the stack. But then at some point I want to be able to maybe transform these two like 2 indices into one index, if you know what I mean. We can try to do the following thing. I can just do dupe2. I think I got it. Did I get it? I think I got it. So let me try to do the following thing. So you have 2 indices, like maybe row and column. Let's call them row and column. So we iterate in row and we iterate in the column. I just dupe those things. And the next thing I need to do, I need to kind of multiply a row by the size of the row. So to do that, I probably have to swap them, right? So what if I swap them? There's no such thing as swap, is there? Okay, there's SVP. So I do SVP. Then I'm gonna push the size of the row, which is A. I should probably use like this kind of thing, but anyway. So I push 10, and then I'm gonna be doing multiplication. Multiplication does in fact exist, look at that. So I do multiplication, that just pushes that thing in here, and then I do add. Okay, there is add, and that adds these 2 things together. I've got an index in here by which I can finally address things. Did I master concatenative languages? Are you impressed? I don't know. I still can't do that, all of that in my head. So I suppose people who program in concatenative languages all the time, they can kind of do that in their head. They can simulate the stack in their head. I remember being able to do that when I was developing Porth, but I have not developed Porth for quite some time, so I think I lost my ability to simulate the stack in my head. So the more you do concatenative languages, like the more you develop that stack simulator in your brain. The Catlang community is impressed. Thank you so much. So this is an index, but that index is simply an offset. It is simply an offset. So what I need to do, I need to now basically add that offset to the board. I need to add that offset to the board. But this is a 1 byte offset, right? So we can kind of say that this is like 1 byte, this is another byte, this is another byte, and this is another byte. So if I try to do something like a board, this thing is going to be actually 2 bytes. No, 16, right? So it's going to be 2 bytes. So I won't be able to just add the thing like that, right? So add 2 probably operates on 2 bytes and so on and so forth, right? Which raises the question, so we need an extra 0 in here, right? We need an extra 0 in here. So, and that 0, so the endianness is big endian in here, right? So that means, yeah, so we need to put 0 somewhere here. We need to put 0 somewhere here. So let me maybe think. Oh, maybe, by the way, maybe I'm kind of overcomplicating this stuff. Maybe. Because maybe I could have just kept a general pointer somewhere here. Nah, that would be actually easier to do it like that. So this is the board. So let me take a look at what kind of adds we have. So where is the UXN machine? Where is the add? So there's the add 2, and yeah, so we literally just work with these two things. Where is my code? I can't see code. I duplicated these two stuff. But now, like, I want to be able to put 0 here. I want to be able to put 0 here, but duplicate is kind of like not going to duplicate the right thing. Or, wait, chat, wait. Can I just 0 swap? I think, by the way, I think I just killed something very important. Yeah, so, yeah. So essentially, so dup2, then I swap, multiply, add, so we got that, and then I put 0 swap, yeah, I put 0 swap, so that gives me that. And then I'm going to do board. I do have a feeling that I'm overcomplicating a little bit, but that's fine. Right. So, and then we do add 2. So maybe, I don't know how to split them well, but essentially I get an address from which then I can read. Then I can read. So again, I have row and column on the stack. So the top of the stack is actually the right. So this is the right. I dupe to them, then I swap them. So I have a row in here. I have 0a, then I multiply it like that, right? Then I multiply it like that. Then I add this entire thing like that, and that effectively is an index, right? This is an index and it's a 1-byte index. Then I put 0 in here, I swap it around, so that becomes an offset. You can think about it an offset U16. Then I put board, which is U16, I add them together, so now I have a board plus offset. Right, I have board plus offset. And essentially now I have to just read it. Does that make any sense? Does that make any sense? I think that's basically what I want to do. Yes. And now, how do I read that? So I suppose it's a LD something. LDs nuts. I really like this instruction. LDs. LD load R. So I suppose LDZ is from the is at the beginning, right? So this is RAM, and then LDR. We're still listening to music. Chat. Why nobody told me that I'm still listening to the music? I'm gonna get the DMCA. God damn it. The music was nice. Okay. Well, I mean, of course it is nice because somebody actually spent time and effort and they're not gonna get paid for that. So I'm gonna get the MCA strike. So, oh no, he found. So you knew that the music was playing, and you didn't tell me. God damn it. How do you read 1 byte? So I think the time has come to go and just read documentation, opcodes, and stuff like that. So in the hello world, wait, we already have, okay. So we do LDA, right. And that thing is already 2 bytes. So that means, yeah, that's what we want to do. We want to do LDA. That gives us 1 byte. That gives us 1 byte, and we managed to read that. Furthermore, now we can factor it out. We can factor it out to maybe a separate word, if you know what I'm talking about. We can factor this entire thing out to a separate word, something like board get, and we can say that row column cell. I feel like a real Forth developer. Oh my god. Isn't that the philosophy of Forth development? Because I remember watching some like a very like, you know, philosophical video by a Forth developer on YouTube, and they were saying that the point is that you write the code that manipulates the stack, and then you realize that you saw a pattern and you can factor it out into a separate word. And that's how you build up the dictionary. And then once you build up the dictionary, you write your code like your poem. Is that what it feels to be a Forth developer? You're not writing code, you're writing poem. That's what you do. That's what you do. I guess, I don't know. I'm not a Forth developer, unfortunately. I just know a little bit about concatenative languages. I wrote one. Not the best one. I can show you what kind of concatenative language I wrote. So Porth. So what do we have? Literally this one. Oh, yeah. So does it look like a concatenative language? I already forgot how to use this language, honestly, but yeah. So this is basically how it looks like. I wonder if I can find proc or main. Yeah, there we go. So this is how it looks like. So this is my concatenative language. You would literally allocate memory like this. That's a very interesting one. So you have while loops and everything. That's a pretty cool one. It's, by the way, it's written in itself. It's self-hosted, right? It's self-hosted. It's written in itself. So you try to compile it with itself, and you get an assembly file that looks like this, right? So you get a bunch of assembly, and it is equal to the executable that you just run. So it's self-hosted like this. Anyway, so I kind of stopped developing a long time ago. I basically considered it an exercise in like how to write self-hosted languages. It was actually very educational exercise. It literally helped me to understand and internalize the Thompson's hack. Right, so Thompson, I hope I pronounced it. I think it's Thompson. I don't remember. Hack. Right. So the basically the piece of code, right, that persists across the compiler. So essentially, you have a compiler that has a piece of code embedded into it, right? So maybe it could be like a malicious piece of code, some sort of a virus, right? And you have the source code of that compiler, but source code of the compiler does not contain that malicious piece of code. You take your compiler, you compile the source code of your compiler, it produces an executable, and that malicious piece of code copies itself to the next instance of that compiler, even though that malicious piece of code never was written in the original source code. So you have a malicious piece of code that persists even though in the source code it's never present, just because it's present in the original executable. And by implementing a self-hosted compiler, I understood how it could be technically implemented. Like, without trying to implement your own self-hosting compiler, you won't even understand like how exactly to pull that off. But now I understand it, and it's actually super cool. This is something that he understood when he was writing like C compiler, I suppose. Right. So for anyone who's interested, like, let me put it somewhere here. The Thompson's hack. Anyways, so we have a board get, and so that means I can just do it like that. Right, so I can just do it like that, and in here I'm supposed to do jump to R, right? So essentially, when I call board get, it jumps here, but it saves the return address on the return stack. So that means I have to return in here. So, okay, that's cool. That is pretty cool. So I also have to do increment in here. And this is where it becomes very interesting. So at the end, I have a column, right? I have a column that I probably wanna right. So I should not forget to do it in here. And okay, so yeah, this is where we're starting to get a very interesting thing. So we can actually give it some sort of a name, columns, right? So this is a columns, and this is rows. Yeah, that's not bad actually. That's not bad. So increment rows. Huh. So yeah, that's pretty cool. Maybe even something like that. Right, so we have a two-dimensional loop, which is probably extremely unnecessary if you think about it. It's probably unnecessary. And the only reason I'm writing that nested two-dimensional loop is because I'm still thinking, like, I'm using mental model of C, right? Because that's what I would do in C. So if I spend a little bit more time with this language, I will probably come up with something more simpler, right? So, but my brain right now just refuses to come up with anything simpler. Unfortunately. Okay, so we get this thing, and the question is, what can we do about that? We can maybe print cell. Right, so let's actually have something like this. Print cell. So we're going to be accepting the cell, and it's going to simply print a character for that cell. Right, it's simply going to print a character for that cell, and the question is, what is it going to be? So the cell, if the cell is 0, right, if the cell is 0, it's probably going to, ooh, this one is cool. By the way, so this thing just jumps to the lambda, but it doesn't update the return stack. That's a very interesting question. I think it doesn't update the return stack. I think it doesn't, but we can look at how the, yeah, it shouldn't probably do that. So if this thing is true, we're simply going to print maybe star. Let's print a star. So ASCII, what's the star? Maybe there's some way to have like a character literals. Euxine Asm. So do we have? No, we don't. I was thinking maybe there is. Wait! I know what I can do. I know what I can do, my friend. I know what I can do. I can do something like this. Yeah. Wait a second. I could never understand what the hell is lit opcode. Let me take a look at the virtual machine. So we have a lit, right? So you have a lit, and what you do, you basically so you take an instruction, but you already incremented the counter. So whatever you're looking at right now in RAM is already the next byte. So essentially, it pushes the next byte no matter what it is. I remember reading somewhere in the documentation of UXN that basically any value, not really any value, but some bytes in a bytecode may be accidentally interpreted as opcodes, which may result in some sort of like effects. So essentially, lead is needed to make sure that you push in a byte and it's not going to be interpreted as opcode. Lead or hash puts it on the stack, while just 0 simply puts that byte there in. Okay, I think I get it. Right. So essentially, if you just put that byte there, it may be a valid opcode. Right, which doesn't mean that you push that thing onto the stack, right? So maybe you just want to write that opcode. In fact, you can probably program directly like this. Right, if you know all of the opcodes, right? If you know all of the opcodes, you can probably program directly like this, and it's just, yeah. You can do that, right? So that makes a lot of sense, right? So that makes a lot of sense. And I suppose if you, let me take a look at the UXN assemble, right? So let me take a look at the UXN assemble. So yeah, you're writing just the bytes without the lead. So that means if I really want to push like a character, if I really want to push like a character, I have to do it like that. So this is not really going to cut it, right? Because it may be interpreted as an opcode. That makes a lot of sense. Yeah, that makes a lot of sense. Like having source code, again, like I'm sorry that I keep repeating myself, but like this is just like a perfect example on everything I keep saying, right? Why source code is the best documentation, just because you can figure out things like that from the source code. I know that it looks cryptic, but to that I can only answer a skill issue. Just learn how to read C. Cheers, by the way. All right. So how do I put stuff into La Console? Okay, this is how we do that. This is how we do this. So I can do something like that. And then I can actually, I can actually do something like this, like return right away. Or if it was in fact 0, can I put space? How do I do space? Okay, anyway. So ASCII. So what's the hex? Hex is 20. Thank you so much. ASCII man page. Like, it's kind of weird that there's literally man page for ASCII. Isn't that cool? Right? So every time you need to like look up ASCII codes, you can just do man ASCII and just like, there you go, here's the page of ASCII things. It's pretty cool. Yeah. I learned that from Dennis Clark, aka Last Miles on Twitch, right? So I never knew about that before I watched his streams, right? So it's actually super cool. I made my own ASCII app before knowing that there was a man page for ASCII. Yeah, it's kind of interesting. And what's funny is that it's probably my most visited man page, believe it or not. So the most visited. The second most visited is probably fwrite, because I can never freaking remember the order of the arguments of these things. Like I can never remember. Like what's the size of the element and what's the amount of element, like in which order they are. So I always have to look up this kind of thing. So the first is ASCII, the second one is fwrite, fread. Always consult on those main pages. Always consult on them. All right, so we just put it like that. Okay, I can do it like this, and then yeah. I didn't have to do the second thing. But yeah, so I suppose that's how we're going to be doing all that. And that's potentially may actually print what I want, except not. I want to be able to also print a new line. So at the end of this entire thing, let's actually say new line. Right, so this is going to be new line, and let's call it maybe break line. So this is a break line, and it doesn't have any effects whatsoever on the stack. And in here, we're going to have a new line. So slash, it's supposed to be 10 or something, right? So, yeah, boy, 0A. Okay, I'm a little bit scared. I feel like it may not work, but maybe it will work. Look at that, it's actually growing, right? So it's a serious program, right? It's actually a serious program. And this kind of stuff, by the way, this could be a macro, actually, if you think about it. Right. Yeah, it's kind of... Some things could be functions, some things could be macros. But if you're using macros instead of functions, and you call to that macro like too much, the size of your executable is going to be growing very, very quickly. So something to worry about, I suppose. So, and the size of the executable, by the way, for this specific platform is important, right? So, because you have a limitation of memory. This is so cool, right? So, you really want to be aware how much code you're writing, because if you're making a thing too complex, you may not even fit into the limitation, into the memory limitation. So you have to be super careful. You have to be aware of that. It reminds me of the challenge that I did, where I was trying to write a game in the MBR bootloader, 512 bytes, PinPog. Honestly, PinPog, I'm gonna give you the link. So it was such a cool challenge, because that's the challenge that completely changed my perspective on programming, honestly. Right, so I would even say that I can divide my programming journey into two phases: before I tried implementing PinPog and after I tried to implement PinPog. Once I implemented, I can quite confidently say that I came out as a different person. 5 years ago, I became a completely different person, because this challenge imposed like a seemingly impossible limitation on me. And then I realized that I can do so much in 512 bytes. Like, I never realized until I actually imposed that limitation on myself. Like, oh my god. So I just realized that how many interesting things I can do with these memory limitations. And I basically woke up to realization how much bloat there is around me. Like, it's just like, if this is enough to implement this much, what I can do with more? How much computing where it's insane. So this challenge literally changed me. Yeah, so maybe after this challenge I became such a simplicity junkie, because I oh my god, how much, like, you know, resources we're wasting. I can do so much in such a little amount of like space. It's like, it's insane. Like, I wrote an entire game that looks like this. It has a kebab mechanics. So I came up with that myself because I was too lazy to check for the collisions, and so you get points if you actually, you know, skewer it. So yeah, if anyone is interested. So let me, did I copy paste the, yeah, already copy pasted, so I'm gonna put that in the description for YouTube people, if anyone is gonna be watching on YouTube. Probably, we'll see. But anyway, so I'm actually procrastinating because I'm afraid to run this thing. First try. So we have unused things. It's kind of interesting is that maybe on reset is not really necessary, to be fair. Maybe on reset is really... I really like these notations for vectors, honestly, right? it kind of reminds me of notation in Rust, where you have like a function and you say, let's put it like exit, and you say that it never returns, sort of. But this, I mean, the vector kind of returns, but I mean, it's just kind of funny, right? So it's a special indication, and it's not really a for thing. I think I'm pretty sure it's not a for thing. It's specifically tal thing. Okay, so it seems to be compiling, and it's doing that first try. So first try, got quarter, haha, haha, did it, yo. I'm unstoppable. I have no idea how I pulled that off, honestly. So, pure luck, I'm telling you. So what's the size of the roam, by the way? It's not that much, actually. Look at that. So I didn't waste that much, that much space, which is already pretty cool. Though, like, it's kind of weird. Why is it star? So there is something in there, right? There is something in there. So maybe, is the memory even initialized with 0 at the start? That's the real question. Is it initialized with 0? So let me check something interesting. I'm going to do the following thing. So what if I put 0 and I'm gonna say print cell, all right, and break line. So failed to assemble ROM. Is it not cell E? Excuse me, where is the compilation? Unknown absolute reference, print cell. Just a second, I think I can figure it out. In console. Would be nice if I... knowing where exactly an error has happened would be beneficial, actually. To be fair, we can say that it's one of the limitations, right? If you cannot find the error in your source code, your source code is too complicated. Make it simpler. Keep it simple. There you go. So that's how we can explain that. No need to report any locations. If you can't find an error in your source, it's too complex. Bloat, simplify it. So yeah, that's how we're gonna explain it. Skill issue, exactly, skill issue. I mean, why not, right? If we're trying to impose limitations to keep things simple, why not? So the question is, so we're falling through. So we're calling to this thing when it's true, but this is not true, isn't it? This is not true. So if I put 1 in here, right, it's space. So it's kind of inverted. Like, and I didn't really expect that. So where is the lambda thingy? So GCI, so essentially the logic is like this. If we have a true on the top of the stack, we jump to here. Did I understand that correctly? Right. So, and if we have false, we fall through. That's the logic essentially in here. That's what it is, I guess. We can take a look at the assembler, right? So we have a question mark. So we have a reference. Make a reference. Okay, so what's this? So this is parts. So, and when we're making a reference, while we're making the reference, we have in a lambda, right? So there's a lambda count, and we are making the lambda. We're making the lambda. So when we have a lambda stack, so essentially we're figuring out the ends of the lambda when we encounter the closing. Yeah, there we go. Then we just, so we have a lambda stack. We take the thing at the top of the lambda stack and we make the lambda. Right, and we make the label. So I suppose, yeah, I guess I'm gonna, so it makes sense for me to take a look at the GCI instruction instead and just try to understand what it does. So it's a conditional jump. Yeah, it's a conditional jump. So we have something at the top of the stack, and if it's not, we're just doing, we're skipping it. Oh, man, what? That confused me a little bit. I never seen break inside of switch under a condition, honestly. I mean, it makes sense, but well, I mean, you can do that. Yeah, sure. I guess you can do that. So I never thought. Why I never thought about it? Right. So wait, yeah, you can do that. You can have a conditional fall through. Yeah, you can have a conditional fall through. Why not? Why not? Who said you can't do that? Yeah, conditional fall through. So sounds good to me. So if it is false, we are yeah. So just a second. If it's true, it's gonna be, we're gonna do a jump, right? So if this thing is true, it becomes false, right? It becomes false, it falls through, and it acts like GMI, which is basically, you know, jumping. If it's false, this becomes true, and we're going further. So because of that, I thought that this thing is going to work, but it literally didn't. So that means I'm not understanding this thing. But I can do the following stuff. All right, so just a second. So this is false, and it is going to print. All right, and if it's true, I'm still don't understand the implication of this thing. So, all right. So let's not question it. So I can just like, I can swap it around, but for some reason it still doesn't make sense to me, honestly. It doesn't make sense to me, but I mean, maybe I'll understand at some point. So yeah, something weird. It's what is going on? So that's but if I say do the it never printed anything. Wait a second. Why? And here I probably want to delete. Yeah. Okay. Figure it out. Okay. So it would be kind of nice for us to initially maybe have something. For instance, I can maybe put 0, 1, 0, 1, 0, 1, so it's gonna be 61. Actually, meine Freunde, meine Freunde, meine Freunde. So we have 10 by 10. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Glider! A glider! That's cool. It's kind of cool that you can just directly like I did that. So that's so cool. That's pretty cool. Yeah, so essentially we are basically printing the board, right? So we do print a cell, but we can now say, okay, print a board. Right, so it's not really accept anything. So it's just gonna be like that. Print a board. Like this. And that will allow us to maybe even do that iteratively. So we may have a process where we sort of compute the next state of the board, right, and keep printing it. So since we factored out this operation, right, so it's very straightforward. Honestly, I would like to maybe go with something like dot, something like, yeah, so we can clearly see the boundaries of the border, right? So we can clearly see the boundaries of the border. So we're going somewhere. We're going somewhere. That's pretty cool. So the question is, how are we going to be computing all of that stuff? Interestingly, so there is some sort of like a clever process of computing the next generation of Game of Life in place, but I'm too dumb to actually pull that off. So what I usually do, I have like a backboard. Right, so let's call it backboard. And I'm gonna query replace 1, 0. Backboard. Yeah, so we're gonna be computing the next generation into that backboard. So I think I would like to make a small break because I feel like I already ran out of tea, and to implement the function that computes the next generation, I definitely need some more tea. So yeah, let's make some break. And all right. So what we need to do, we need to be able to maybe count the neighbors. One of the things that you want to be able to do when you're implementing Game of Life is knowing your neighbors. Know your neighbors. So yeah, the question is, how can we do that? So maybe we can have a function that is literally called count neighbors. To be fair, neighbors is a very annoying word. What I like to do, I actually like to call it neighbors. Right, neighbors. Jump to R. So, and essentially we can say that maybe it accepts row and column, right? So it accepts row and column and will just return your count, right? It will just return your count. So, and essentially how we're going to be doing all of that. So it's rather straightforward, honestly. We can do dupe2. Ooh, this is fun. Right, so I can just check like the board get, or maybe get cell. What was the function? I think it was board get. Yeah. So to be fair, I don't really like the convention that we have in here. So I have a print cell, and a board get returns cell. maybe I could rename it to something like board get cell. Maybe that is a better name for this kind of stuff. Right, board get, yeah, board get cell. So, and in here we have a board get cell. And that thing, as we know, takes the pair of these things and returns you the cell. And what we can do, we can essentially increment something. Like, I don't even know, like, what's the best way to do that? What's the best way to do that? Can we have some sort of a counter? So what if we... So what stack operations do we have? I think I need to take a look at the stack operations. So we have opcodes, and so this is break, this is GMI. So pop. It's kind of like, I really like how you augmented sign language with opcodes. There's something interesting about that. So I suppose it was for accessibility. I'm not 100% sure. But at the same time, it has a really interesting implication. You can pass ROMs in silence from one person to another through a sign language. So think about that, right? So it's just like nobody can hear anything, but you have a person in the other room, right? So, and you just like passing ROMs to a different person, just like, and they then write them down, they run it, and they just like save the world or something. Just like imagine that. It's kind of interesting if you think about this, like the implication of like having a sign language for opcodes. Isn't it cool? I think it's pretty cool. So yeah. What do we have? So we have pop. So I don't remember nip. Nip is just like you're removing the one that is underneath the top, right? So you have a swap, that is fine. Rotate. Oh, rotate could be actually useful. Rotate. I love rotate. It's my favorite. So when we are rotating, so you're rotating to the left. Yeah, I see. So basically you just to the left and A kind of overflows and becomes here. Which is something that we could use probably. So there's also rotate K is interesting. Rotate K, so it just kind of preserves it. So duplicate is understandable. Over, you just take that. Equal. I'm just thinking what's going to be the best way to keep track of that single count, right? Because what I was thinking is that maybe I have dupe, and then I would have something like left, right? And essentially left is going to accept this thing and return you this thing, but it is going to increment, I suppose, actually not increment, but decrement column by 1. You know what I mean? Right, so you duplicate, right, so you have row and column, you duplicate them, but then you do left, and that, you know, updates one of these things. Then you do board get cell, right, that gets you the cell, the neighboring cell, and then you add that cell to some sort of a counter. But where do you keep the counter? That's the real question. Where do you keep the counter? So I have a feeling that I don't even know what's going to be the best way to do that. Maybe the best way to do that is to store that counter somewhere in the memory, or in a return stack. Like, why not keep it in a return stack? Yeah, we can do that. We can keep it in the return stack. Who said we can't do that? So, and if I want to push something on the return stack, I can basically, okay, so this is 0, and how do I transfer a thing to a return stack? My Chromium is dead. Huh? Oh, I accidentally pressed something weird. So it's something like STH, I think, moves the value at the top of the stack to the return stack. Okay, so I can do STH. So I put 0, then I move it to STH, and now I can do things there. So that allows me to... Aha! Isn't it poggers? And you just like need to implement all of this like left, right, and you also need to do diagonal things. Though not necessarily. You don't really need to do diagonal things in the sense that, okay, so you have left, down. You can always do something like left down. Wait, what the hell? That is so good, cool. So left down, right, left down, right, maybe left up, right, left up, right down, right up, and that's basically it, I think. Right, that's basically it. So so then you move this thing back and you return from there. Isn't that a cool way to do that? Wait a second, like, come on. That is so cool. Like, I keep I forgot about the second stack. The second stack is actually very useful, right? So you can do things there. This is actually readable. I'm still not sure about the name for this thing. What if we, like, it's too long, honestly. It is too long. Nah, let's keep it like this. Let's keep it like this. So, and when we have the left, right, so jump to R. Jump to R. It's rather straightforward. You just decrement, and that's it. So, and in case of right, you just increment. Okay, so if you want to do up, so up is minus row. I know, by the way, thank you, chat. Thank you. That was good. So wait, there's no such thing as deck? Are you serious? I do not believe you. Yuxi and deck? Nah, that can't be true. What is it called? Deck. So is it increment? I mean, that makes sense, right? So, yeah, you need to know tooth complement to actually use this thing. Well, you need to have a lot of knowledge about computing to use this thing. That's kind of interesting, actually. It's really, this whole project is interesting and deceiving at the same time, but not in a bad sense, by the way. Not in a bad sense. It's just like, it feels like it's a sort of like a, you know, like a language for school and just like for kids to learn programming for the first time, but the depth of the knowledge you need to have to just use it on a basic level is kind of very interesting. And I wonder if that's intentional. I think it's intentional. I think it is intentional. It's kind of really interesting. Because I mean, yeah, so it does support negative numbers, but you need to like know 2's complement. Like it's not a really like a basic knowledge. It's a pretty advanced knowledge in my opinion, honestly. So, oh yeah. I mean, sure, I can just do that. So we just add negative. Yeah, the Q-derms are deceptive. Yeah, they are. So we use 2's complement. So if you wanna, wait, there was like a negative, I think. Oh, there was a, yeah, so they're not equal, but there's no negative. And if you want to do negative, you probably want to do that yourself. You need to invert bytes, right? So if you have some sort of a number, right? So you just push some sort of a number, or I don't know, like, yeah. Let's say I pushed 10 and I want to get minus 10. I need to invert bytes, but to invert bytes, I need to do XOR, right? And add 1 inc. So, well, technically, you can even do something like, I don't know, negative, and just do something like that. You can implement your own instructions, essentially, right, out of like the basic things. I guess you can do something like that. But yeah. So we're gonna do up, and this one is swap. So up is just this. Yeah, up is just this. Swap, ff add, swap, jump to R, and then down, which is just add. So in that case, it's just increment swap, increment swap. So we have these things. So we get the board, right? It's just like, yeah, that should be it, essentially. That should be it. Interestingly, we don't really have a way to print numbers, right? So if you want to be able to print a number, you literally can't do that. Or can you? That's an interesting question. So essentially, well, as so I have the following thing. Like I have a number. I can duplicate it, grab its first digit. I can grab its first digit. And I can push it into the return stack. I can push it into the return stack. So this is basically the working stack. This is the return stack. Right, then I can divide it by 10. Then I can do that one more time and then push it on the return stack and divide it by 10 again. And essentially, I'm gonna be having it in the return stack in a reversed order. So which makes it kind of easy to implement the something like a print number kind of thing. Print number kind of thing. Though we know that we're not gonna have a number that is oh my god, so that is bigger to 256. We can basically hard code all of that stuff. We can hard code all of that stuff, or maybe even print hex, which accepts a number, right? but it would be way easier to actually do dec. Yeah. So what I want is maybe duplicate this thing, then divide it by 100, right? So what's 100 in hex? Okay, so 64 divide. So that's I suppose how it's done. Then what I want to do, I want to maybe add 0, right? So add 0 and then print that specific character. Right, so I print that one, then actually if I'm gonna be printing so yeah, 256, if I divide it by like 100, I just get that. All right, so that's perfect. The next one I duplicate and I want to divide it by 10, but then I have to get the mode of 10. Do we have mode in there? Do we have mode? So where's UXNC mode? There's no mode. There's div. I remember there was div, but there's no remainder or anything like that. So there's no even dollar. I see. I noticed, I already noticed, thank you. So, but maybe I just do that incorrectly. Right, so I want to do decimal, but maybe as just like I need to do hexadecimal instead. But maybe not. Okay, let's actually not waste time on that. Right, I don't think it's worth doing it this way. So this is down. This entire thing should already work, I think. So one of the things we can do, we can take a look at the index like in here, right? We can take a look at the index in here. On reset, where's, or at least, yeah, there we go. So 1 1 count neighbors, or what was that? Yeah, it was count neighbors. Emacs doesn't autocomplete. Bob. Oh my god, neighbors. Bobbers. So, and then we can just like do the usual loop, right? So we can do the usual loop. So if that's the thing, we can do dupe. And how to say that? So we want to invert this entire thing, right? So so print board less than. I still, this particular thing still kind of confuses me. If it's less and it's not less, so there's something with lambdas that I do not fully understand, so I'm not going to be using it. Right, so we can do over. I still have a feeling that you need to have main label. You need to have main label if you have sub labels. So if it's true, so that means you can't really like easily invert this thing. So we can check whether it's greater than 0, I suppose, right? So we can put 0 if it's equal to 0, right? So Where is the equality? Equal, yeah, EQ. So duplicate equal to 0, it's over. Okay, so I managed to do that. So the lambda with the question mark, it's kind of confusing. I still don't fully understand it, but I want to use it at some point. Right, so in here, what I want to do, I just want to print hello world. So this is going to be hello world, print text, right? Print text. And then we simply decrement, right? And we know that to decrement, we have to do that. Right, and then we do again. Okay. So first of all, let me check whether this entire thing works. If I put 0 in here, right? If I put 0, is it going to perform? Okay, so if it's 1, 2, okay, it tells us. So now, if I count the neighbors correctly, we should see exactly 5 hello worlds, and we didn't see anything at all. We didn't see anything at all, which is rather interesting. So if I just do something like this, so maybe one of the things I have to do here, by the way, is also pop 2. I completely forgot about that one, right? So I also need to pop 2, but I don't think it's going to sort of like solve the, yeah, it doesn't really solve any problems in here. So let me put it like this, and I'm gonna put 0, 1 in here, right? So it is 1, it does return correctly, so it does return 2. So I'm moving this thing to here. So we definitely don't have any, right? So here is 0. I'm moving the 0 into the return stack. I'm moving the 0 into the return stack. Then I'm popping it out and I'm returning it back. Right, so that works. And if I'm doing it like that, it's 1 hello world, it's 2 hello worlds. That seems to be perfect. Interestingly, so if I do something like this, move it to here and add it, that is 1. No, so here is the problem. So I push something here, I move it to the return stack, and I completely forgot R. That is cool. So that's basically what the kind of the problem we have in here. Alright, so that's pretty cool. That's returning back, and there's 2 of them. Okay, so which is again incorrect. We're supposed to have 5 of them, right? So we're supposed to have 5 of them. That's kind of interesting. Right, but again, I just want to double check some other things. So 0, 1 sthaddr. Right, so that's 1. That's 2. That's 3. So that means that particular pattern works correctly. That particular pattern works correctly. So we can try to see if I go to the left, it should not increment. Yeah, so that is true. Do we have at left down? So we do in fact have at left down a thing, right? So if this is 1, 1, left down, so we should have 1 neighbor there. We should have, yeah, this is true. So left up, we should not have anyone. Okay, that's cool. Do we have anything at the right? We do have something at the right. That is true, because that's the glider. Right down, we do have something at right down. That is true. Right up, I think this is one of the cases when we, yeah, right up is this one, so we don't have anything. That is true. Up, what about up? Do we have something at up? Yes, we do. That is cool. Do we have something at down? Yes, we do. So that entire thing must work, and something is fishy. So there's still 2 in here. Is that because it cannot process? the you know, 5 of them or more than 5 of them, I can always do ADDR. So where is the mistake though? So if I have 5 in here, so it is true. Okay. So is there something incorrect in get cell? When I do get cell, so I dupe those things. I don't have to dupe them, actually. I consume them, don't I? And when I do get cell, by the way, this is where I have to dupe them. Right. And yeah. So I consume them. There we go. I fixed the problem. Who needs debugger? It's not even a printf debugger because I don't have a proper printf. I literally have one function that prints hello world and I debug with that and it fixes the problem. There is a debugger. God damn. Okay. But I mean, I don't need it. I can debug with hello world. This is more fun. It is indeed fun. Right, it's sort of like a binary search. You're basically bisecting the problem, right? So, because this is literally what I was doing. I was bisecting. I was trying to figure out where exactly the bug occurs, right? And I kind of nailed it down, and I found that it's like somewhere around like a, you know, board get cell. So I think we managed to do that. So this entire stuff doesn't take into account wrapping around. Should it though? That's the real question. Should it though? And usually I do wrapping around by by mod, but we don't have mod. Oops. We're back to mode. Though, you know what? We can do some magic in these left, right, up, and down functions, right? So essentially, we can just like literally make a condition. If, so for example, column is 0, right? So we're literally gonna set it to the right edge or something like that. So it complicates it a little bit, but I mean, I think we can figure it out. I think we can, in fact, figure it out. So if it's, yeah, so we just incremented this thing, we can duplicate the right column, and if right column is greater than the edge, right, so how can we do that? So DAH. So we can, man, the lambdas confuse me. I want to play with lambdas a little bit more. I'm sorry. Like, I really need to understand how this conditional lambda works. So we can actually factor this thing out. So print text. So we can say print hello world. Yeah. N times. And we can do something like this. So which is a rather useful function to have. Print hello world n times. So print hello world n times. It's times. Okay, so that's cool. So that means here, if I have like 2, it's not how you do that. This is how you do that. Yeah. So that's a very useful function for debugging. It's a very useful function for debugging. So I have this thing. So where I can just print hello world. It's kind of weird that Emacs doesn't autocomplete any of that stuff, even though it can find this function here. So the mode kind of messes up autocompletion for whatever reason. So when I do something like this, I think it's literally not going to do anything. It's only when I do something like this, it kind of falls through and performs this thing. So if I have 1 in here, it ignores it. If I have 0 in here, it actually falls through. So what's the meaning of question mark in here? So it's a conditional jump, but it's a conditional jump to the opposite side. So that's what it is. It's a conditional jump to the opposite side. If it's true, skip. So that's the meaning of this thing. And for some reason, it messes up with my brain. I swear to God. I don't know why. It's just like, yeah, because when you're doing this kind of a conditional jump, you jump when it's true. So the action, when it's true, perform the action, right? That's why. When it's true, perform the action. And in here, my brain thinks, okay, if it's true, perform the action. If it's true, perform the action in here. Maybe I'm just thinking about it incorrectly, but I don't know why it just messes up with my brain. Right, so maybe I should switch the way I think about this thing. If it's true, jump to the opposite side. That's probably what it is. That's probably what it is. So what I was doing, I forgot what I was doing. Right, so we have counting. Yeah, so I was trying to do wrapping around. So I was trying to do wrapping around. So when we have 0, when we have 0 in here, we can do the following thing. Yeah. So this is 0. We just pop that element and we push A, but we actually have to push 9 because it's A minus 1, and we can kind of do the following thing, right? So, because I want to explicitly use the, the width in here. And by the way, this particular width is actually occurs here way too many times. Maybe the time has come for me to like really factor it out to a macro, right? So I can have width and let's call it size actually. So this is size, and this is gonna be 0a. So that's the size. Unfortunately, I can't use it to allocate this kind of stuff, but maybe that's fine. Maybe that's fine. So, and every time I refer to these things, maybe I should refer to this stuff, right? So this is the that's absolutely accidental, right? So the new line is also 10, like I didn't think about that, but yeah. So print board, it's the size, then get cell, then the size, yeah. So in here, let's do print board. So let's just see. Okay, so that seems to be working. We didn't break anything. So now, if I duplicate this entire thing, and if it's false, it will fall through. It will fall through, and what we'll have to do is, I guess, pop and replace it with size, but maybe I can have a deck. You know what? Who said I can't have that? Yeah. I can do that, actually. So That's another one. That's another one. There we go. Deck opcode. Get, yeah. So if this thing is 0 and you're trying to decrement it, we're actually gonna to be fair, damn, look at that. Look at that sexy code. Haha. That's pretty cool. Anyways. So let me think. That's very cool actually. So it's it's basically wrapping around. This one, if it's, we need to check if it's greater. All right, if it's greater than that specific thing, we can take the size, but we can check if it's equal, right? So because when it overflows, it's gonna become equal, right? So it's gonna be EQU, right? So it's equal to that, and if it's kind of true, right, so we have to kind of invert that. We have to invert that, and if it's true, what we're going to be doing, we're going to be popping it and replacing it with 0. So it's kind of the other way around, effectively. It's kind of the other way around. So increment, is it equal to size? And also you have to invert. You have to invert. And I'm thinking maybe I'm gonna factor out invert as well. But if a logical invert is not exactly, wait. If it's, yeah, I can do it like that. Right, essentially, if it's not equal, skip that. If it becomes equal, pop that and replace it with 0. So that's basically what we have in here. That's basically what we have in here. So this one, up, is kind of similar. So that means we can repeat this logic for the up. We can repeat this logic for the up. And that means in here, like down is kind of similar to right. That means we can repeat this logic for down. It's literally the same code, except they are wrapped in by doing swap, we are rotating our dimensions. So essentially, yeah, when you swapping, you're rotating your square and you're using left and right and you're rotating it back. So that is so funny. I don't know why it makes me laugh, but I mean, it's just like, isn't it kind of funny how you notice this patterns and it's just like they kind of make sense? It's actually, is that because it's inherently concatenative thing? Is that, I think this is because it's a concatenative thing. I think I would not think about this kind of stuff in a classical, like, structural programming language like C or whatever. I think it would not occur to me. I think this, like, concatenativeness enabled that. Oh, that's very cool, actually. That is very, very cool. So left is decrement and right, so yeah. All right. And yeah, so we already have our flow. That's what's cool about it. We already have our flow. That means count neighbors automatically checks for the overflows and just like, yeah. I think it shares some properties to Hilbert curve and the likes, which are very concatenative in nature. That is true. It kind of like it does feel like Hilbert in a sense. I see what you mean. I actually see what you mean. Damn. That is so freaking cool. Anyways, so let me see if all of that still compiles. Maybe it doesn't compile. It still compiles. Would you look at that? We have some unused labels, but I mean, that's besides the point. And the macro system is rather useful, right? So it's very much limited. You can't have parameters, but I mean, why would you have parameters in a concatenative language, right? So you don't need that, right? So you just need to be able to collapse a bunch of tokens into a single token. So, okay. So now what we need to do, we need to basically compute the next state, right? So that's what we want. We're happy to say that you're no longer under investigation. I developed a self-hosted, statically compiled concatenative language. How am I under investigation in the first place? You know how hard it is to implement statically typed concatenative language? You know how hard it is. So essentially, I was doing the WebAssembly style verification, where essentially you do meta evaluation of all of the control flows, and basically push on the stack not the values but the types. But I actually did a more complicated thing than WebAssembly. WebAssembly has the structured blocks, which makes it super easy to kind of check for that. I didn't have structured blocks. I literally have gotos, right? So, and what I had to do, I had to have an exponential algorithm that simulates all of the control flows and make sure that different control flows merge with the same state of the stack. Think about it. I simulate at compile time several control flows that meet at the single point, and I make sure that they end up with the same state of the stack. And the initial algorithm was exponential. I managed to actually improve it to a linear one. So, and I had to like develop a special persistent data structure that keeps track of all of the stacks of all of the control flows simultaneously and reuses parts of them. And after that, I'm under investigation for not liking concatenative languages? Seriously? I'm sorry, I'm joking. Like, that algorithm that I came up with was so cool, I was thinking to write like a paper about it, because like, damn. I never thought I would come up with something like that. I should definitely write a paper about it. So as far as I know, that algorithm is not really something new. And it already existed, but somebody invented that algorithm in kind of like a slightly different area. I think it's a very common thing. Damn. Yeah, I think I reinvented a very common thing. It's called something like a tree of stacks. I think that's what it's called. Tree of forest of stacks or something like. Forest of stacks. So forest stack climb, no, not really. God damn, I don't remember, but yeah, so it's basically a persistent data structure that is kind of like a directed graph, but it's also keeping track of several stacks simultaneously, if that makes any sense. Like, there is something like that. People have invented this thing before me. It's kind of like a cone cell stacks. Yeah, exactly. Maybe, let me Google it up. So, but the cool thing is that I reinvented it myself, so so that's what makes it special for me. I think that's what it is. Yeah, maybe, I'm not sure. Is it highly influential virtual machine? No. It was specifically data structure. Anyway, so I should probably find it at some point. Anyway, So to compute the next thing, we just need to iterate the board yet again. We already know how to iterate the board, so there you go. We already know how to iterate the board. So, but here we're simply I know a cool shit, chat. I know about lambdas. I know something about lambdas. So lambda can be used to store data such as stack amongst the GSI lambda assembles to subroutine that puts a return address, or in this case the location of the data memory, and return stack. So I know that if you do something like that, you effectively get a lambda on the return stack. So you kind of need to do something like this, and what you have effectively is an address to this lambda. This lambda was never called because it was skipped, but now you have an address to this lambda. Can I have a function iterate board? STH to R, iterate board. I don't know how to annotate that, but I mean, so if I, yeah, so it's essentially here, you have a row and column, and you don't have to worry about that. Yeah, you don't have to worry about, so you have a row and column, and at this point you can just do count neighbors, right? You probably want to dupe this entire thing, or maybe we assume that you consume that thing anyway. So you count neighbors, and in here, depending on how many neighbors you have, well, I mean, actually, you dupe to board get cell, right? And then you count neighbors. So on the stack, you have two things: the current state and how many neighbors you have. And honestly, that just means that I can count neighbors like later. Okay, so I can first count the neighbors and then get the cell state. So first I check whether we're alive or not. That's what I do. So if I'm alive, right, so this is where I'm alive. So if this is true, I will skip that. So that means here I'm alive, here I'm dead. Jump to R, jump to R. Right. And what that means that here I have the neighbors. I need to check. So if I'm dead, when I, you know, go to life, game over life. Also known simply as life, is a board game originally created in 1960 by Milton Bradley, the checkered game for life. Classic. Classic. Conway's game. Sure, of course, of course. Any dead cell with exactly 3 live neighbors becomes a live cell as if by reproduction. Why not? Why not? So 03 EQU, and in this case we can even do something like this, I think. Dead, alive. And if it's true, ooh, this one is interesting. So we need to be able to set a particular board. We need to be able to set a particular board. In any case, so I'm getting into like a very complicated territory, but I think I roughly outlined what I want. I'm not sure if this idea for iterating a board will work at all. So I first want to check that. Right. So yeah, essentially, how do I call something that is on the stack? I guess we have things like GCI, which is a conditional jump, immediate jump. So what is GSI? Is that what I think it is? Is that what I think it is? So let me take a look at the opcodes. Jump stash return instance. Aha, pushes to the return stack, and so that's what it is. That's what it is. So it basically, if you have on top of the stack some sort of address that you want to jump to, you can use this instruction and it basically calls that thing. So, and if you have some sort of a word, like iterate board, it compiles down to pushing the absolute address of this thing and then calling GSI. We can even confirm that by looking at the assembly. Right, so if we encounter some sort of a word, so opcode, we're not interested in opcode, row byte, macro, and now we have a make reference. I think maybe that's what it is, make reference. If it's a label, find label. So we find the label, all right, so we're finding the label, and then we're copying it, though I'm not really sure. So maybe I'm not looking at the right thing. Well, I think I am looking at the right thing. I would expect the call to be somewhere here. Right, so this is the macro. Wait. Are those the bytes that perform the thing, the call? So make a reference, so that means we kind of push the reference, right? If we find the reference, I think we kind of copy the reference maybe. And if I take a look at the UXN, UXNC, so do we have 60? And 60 is a freaking GSI! I cracked the code, I understand. Literally, if you use the label directly, it compiles down to pushing the reference and then doing GSI. Not sure about this thing, like what the fuck is that thing, but I mean, whatever. So, is Mojo gonna replace Python? You know what's gonna replace Python? I'm gonna show you what's gonna replace Python. This thing. This is the future of AI programming. I'm telling you. All of the modern AIs are gonna be written in this language. You know why? Because in a post-apocalyptic world, you're not gonna have huge data centers to run your Mojo. So all of the AI is gonna be written in that. Welcome to the future computing. Anyways, so yeah. Iterate board. So I'm just thinking how I'm going to approach that. So if I get the function, so I'm getting the lambda in here, right? So I'm getting the lambda in here. I suppose what I want to do with that lambda, I want to do STH, but I want to do STH too. So I'm going to move the entire thing there. So when I'm printing the board, I'm doing this thing, right? I'm doing this thing. So by the way, this has to be GMP to R. All right. So, So well, this is kind of annoying in the sense that I won't be able to implement print using this thing because you need to have extra code to break the line. So you need to have an extra code to break the line. So maybe you're gonna have like 2 things in there. So yeah, I feel like so the reason why I want you to have iterate board is because I want you to reuse the same piece of code for print the board, and for compute the next state. But for print the board, you need 1 extra additional piece of code, which is breaking the line, which is kind of annoying, honestly. So which means that I can't really factor out iterate board that easily. But maybe I didn't have to, right? So let's just copy paste, right? So let's just copy paste. I think there's nothing wrong with copy pasting. It's kind of a cool idea, right? To have this sort of functional style. But I mean, maybe it's going to be reserved for something else, right? So it's going to be reserved for something else. So yeah. I would like to maybe make another break, honestly. So I'm already streaming for 3 hours, but I'm almost there, actually. I'm almost there. So I need another cup of tea. So let's make a small break. I'm gonna make another cup of tea and we're gonna finish this because we're almost there, right? So just look, we have all of the necessary mechanisms to do the thing. Right, so all right, I got my tea. So we are now iterating the board, right? So we're just iterating the board. And in here, what we're trying to do, so we probably first want to, as already said, count the neighbors, right? Count neighbors, and then get the cell. But we don't have to print anything in here, as you can see, right? So we don't have to print. To be fair, so do we need to duplicate? Yeah, we do need to do the duplication. So if the cell is alive, right? If the cell is alive, what do we have to do? So honestly, what we have at the top of the stack is just the count and the cell. So we have 2 numbers in here. What we have to do, we have to now transform it maybe into a number, right? So maybe into a number that we can then somehow consume. It's kind of interesting. So we could just have a function next cell. All right, so we can have a function something like next cell. And what it does, it accepts the count, and the cell, and just returns you next cell like 1, right? So it returns you the state of the next cell. So we have not applied it yet. I don't know what the hell is going on in here. Let's put to do. And essentially afterwards, what do we have in here? We have row, column, and cell 1, right? And basically what we need to do, we need to save that new cell to the backboard, to the sort of next board. So the question is, how can we even do that? The problem here is that I need to not lose this row thingy. I need to not lose this row thingy. So initially, I have a row column. What I'm thinking is that I can duplicate it an extra time. Right, I can duplicate it an extra time. So I do the first duplication like so. All right. So then I duplicate it again and turn it into count. So that's basically what happened in here. And this is where, yeah, so this is not going to work that easily. Yeah, so this is kind of the problem. So I need to probably have a rotate. So how do we do rotate? So that takes this thing and brings it to the top, right? That takes that thing and brings it to the top, which means I see what is going on. I see what is going on. So we can maybe do the following thing where we consume the count, right? So if the count is 0, right, the count is 0. Yeah, so I'm repeating the thing that I was trying to do, right? So repeating this thing that I was trying to do. So that's basically the thing. If it's 0, it's gonna fall through. That means it's dead. Right, so let's just do that thing over again. It's dead. Otherwise, it is something else, but So I'm actually already tired. But I really want to finish it. I really want to finish it because it's almost there, right? It's almost there. It's just like, ah, man. And so maybe I can push through. Maybe I can push through. Okay, so let's actually push through. So we need to duplicate whatever we're doing and just do next cell. Okay, so let's reform the notion of the next cell. It's going to be a row column and it's going to update this entire thing, right? So it's going to update this entire thing. So yeah, this is going to be that. Dupe to no, okay, so I'm already streaming 3.5 hours and it's already too much for me. I think I'm gonna stop here. Stop here and we're gonna continue this thing tomorrow. Right, and tomorrow we're gonna finish all of that stuff, right? So I'm gonna implement the computing of the next state, and hopefully I'll also implement the graphical part. I think graphical part is going to be also important. And I'm going to concatenate the all of that into a single VOD as I usually do. All right, so that's it for today. Thanks everyone who's watching me right now. I really appreciate that. Have a good one, and I see you all on the next recreation programming session. I see you tomorrow. Right, tomorrow we're going to continue all of that stuff. Love you all. Mwah. All right, so this is the next day. So let's go ahead and continue developing the game of life, right? So here we have a loop that iterates through all of the cells and stuff like that. I really don't like how cryptic it is, right? So it's just like, who knows that this is basically a knot, right? So essentially we duplicate the iterator, right? Then we push a size and then we're checking that this iterator is less than a size, right? But since this thing jumps to the opposite label when it's true, we actually don't want to jump, so we negate that true to false, and because of that execution falls through. So this is basically the logic. So what I'm thinking is that maybe we could come up with something like, I don't know, not, right? Because I know that not is not is not an opcode in UXN. All right, so it's not an opcode in UXN. So there's no such thing in here. So we might as well just go ahead and factor it out, right? You know, the usual thing. It's very common in concatenative languages to just notice a particular pattern, and just factor it out, like so. But here's an interesting thing. That not only works when your true is equal to 1, right? But as far as I know, the jumps, conditional jumps, are more like how the web developers like to call it truthy, right? So I think web developers came up with this beautiful, beautiful word called truthy. Because I've never heard that word outside of web development, honestly. I've never heard that word outside of web development. It's only the web developers that name it like that. So the idea is that 0 is false, everything else is true. Right, so 0 is false, everything else is true, and we can see that in the implementation of the virtual machine. Right, so here's a conditional jump, and t is the top of the stack, and if it's basically not, if it's true, right, so if it's actually true, it's going to be false, so it will actually perform the jump, so it's not going to perform this condition. So yeah, essentially, we want our not to be aware of truthiness. So what I'm thinking is that the easiest way would be to just say equal to 0, I think, something like that. Because essentially, if you have 0 and it is equal to 0, it's going to become true. If you have something that is not 0, right, so maybe negative number or positive number, doesn't matter, it's not equal to 0, so it's going to be false. So something like that is better, so it's actual logical not, I think. It is actual logical not. So let's actually see if it works or not. So I'm going to go and find the other places where we needed to have not. So this is another one. This is where we sort of print the board. And now it's a little bit better, I think. Now it's a little bit better. So I have, you know, the iterator, then the size. I check whether like iterator less than the size, and I take negative of that. So basically, while it's greater or equal, right? If it's greater than equal, then basically skip this entire body, right? But if it's not, it's actually going to fall through. I think that's the logic in here. So let's actually double check if this entire thing is going to work. So this is basically like a loop that tries to compute the next state of the board, right? So we don't really want to have it right now. Let's just print the board. Does printing the board accept any parameters? No, it does not. As you can see here, we have nothing. And let's just try to compile this entire thing. So of course, the ROM is located, the assembler is located in here. There we go. So we managed to compile everything. 453 bytes. 69% used, 69% used, nice. But anyway, bloat, we're slowly getting to 1%. We're slowly getting to 1%, so I don't know, we're getting bloated, more bloated and bloated, so we have to be really careful with that. So I suppose we only have like a 64 kilobytes, right? So, and I suppose like the program itself is also stored in the memory. So that means the more code we write, the less data we can store. So something to think about, I guess, right? Something to think about. And also maybe the code part is also limited to some extent. I don't know the actual technical limitations of the UXN virtual machine, right? So I can look them up, but I'm too lazy right now, so who cares? I'm not gonna care until I actually bump into the limitation, right? Before that, I'll just, you know, keep piling code. So after that, after we compile this entire thing, I'm going to do UXN CLI, right? UXN CLI, goal ROM, and boom, it's working. So now we have a proper not, right? We have a proper not. And now when I look at that specific loop, it doesn't fucking blow my brain off, right? Because at least I can read it. It's kind of an interesting idea that essentially UXN implements like a bare minimum of instructions, and if there is an instruction that can be implemented in terms of other instructions, it doesn't do that. it's kind of interesting, right? So like there is no such thing as not, because you can implement it like that. There is no decrement because you can just add a negative number, right? So it's kind of funny. Like, why would you need a sub instruction? Yeah, so like you don't need a sub instruction. You don't need a sub instruction. Thank you, Mr. Botka. You're right. So. And it's kind of cool. And on top of that, the language gives you a system of macros, so you can basically wrap these, compound instructions into new instructions if you want to. Right. So that's kind of cool. I think that's pretty cool, actually. But there is sub instruction. There is sub instruction. I don't remember. Wait. Oh yeah, there is sub instruction. So the author of the program was actually trolling me. Okay, the author of the program was actually trolling me, so I suppose, yeah. Anyway, so well, in that case, we're gonna continue doing that. Like in that case, we're gonna literally continue doing that. If the author said so, right? So we're gonna do that, right? Because that's the official, that's the canon way of doing that. All right, so let's go ahead and see what we can do in here. So here we're obviously iterating through all of the cells, right? So two-dimensional loop and everything. And so here I basically came up with a function that I expect to compute the next state of the cell. So essentially, it's going to accept the row and column, right? And then look at the current cell in the board, right? Look at the neighbors around and stuff like that. And then it's going to write the next state of that cell into the backboard, right? So that specific function is supposed to just look at the current cell and compute the next cell in the backboard. And then we're going to separately have a thing that basically copies backboard back into the original board so you can repeat the process. Right, so this is basically what can happen here. Right, that's going to be the idea. So, yeah. And the first thing we want to do, we want to know whether we are dead or are we alive. Because depending on whether we're dead or alive, we're going to just actually treat the neighbors differently, right? So if we're dead, we are ignoring our neighbors. If we are alive, I don't know, we're bothering our neighbors. So let's duplicate this entire thing. And so board get cell. Is it just get cell? Yeah, so it's a board get cell. Board get cell, and if it's true, right, so that is going to skip this entire block. So that means we're only going to get into this block if we are dead. And we can sort of like a short circuit the execution of this entire thing, like so. We're short circuiting it. So that means here we have alive. So essentially it turns into sort of like a if else, right? So here is the then branch. This is the then branch, and this is the like else branch. But I think it's more like unless, right? Because if it's true, it's going to go in here, right? So it's going to go in here. So basically like that. So after that, we probably want to take a look at the neighbors, right? So we're going to duplicate this entire thing yet again. We're duplicating it, and then we're going to count the neighbors. So if we are dead, a game of life. So I actually need Wikipedia, by the way. Game of life, Wikipedia. Maybe Conway's game of life. Conway's game of life. So if the dead cell with exactly 3 neighbors becomes alive as of reproduction. Okay, so essentially we count the neighbors and we want to compare it whether it's equal to 3 or not, right? So this is going to be EQ. So if it's true, if it's false, nothing is going to happen, right? So that means, right, so new cell dead. It stays dead. Right, new cell stays dead. Jump to R. Otherwise, new cell alive. So that's basically what we're doing here. That's basically what we're doing here. So the question is how exactly we're going to do that. We already kind of have a row and column at the top of the stack. So that means we may want to like put 1 in here, right? So we're pushing 1 and we need something like a backboard set cell, right? So and effectively backboard set cell is a function that is going to accept a row and column, and we do have that thing at the top of the stack and this cell, right? And it's just gonna set that entire thing like so. Otherwise we setting 0 in this entire thing, right? Something like this. So that's pretty cool, isn't it? And that's pretty cool. So we're essentially dead. So we look at the neighbors. If it's exactly 3, we set, you know, backboard set cell to 1. Otherwise, we set it to 0. Very simple, very straightforward. So essentially, we're looking into 4 possible situations. Right. And now, if you are alive, you need to take a look at the neighbors as well. And I suppose neighbors has to be, if 2 or 3, you stay alive. If neither 2 or 3, you become dead, effectively. So this one is going to be a little bit more complicated, I think. It is going to be a little bit more complicated because we counted the neighbors, right? So if it's equal to 0, all right, if it's equal to 0, we have to also check it if it's equal to 3. So what's the easiest way to actually do that? So let me take a look at the state of the stack. All right, so in this, on the stack, we have a row column, then we do dupe2, so that works like this. Then we count neighbors, and we get neighbors in here. Then we do 0, 2, and we do equals, right? So that gets rid of this entire thing, and we have just like the first condition, so condition 1. So what I'm thinking is that, is there EQK? Is there EQK that basically keeps the things? Or maybe not necessarily, right? So maybe not necessarily. What if after we counted the neighbors, we just dupe the neighbors, right? So now we have this amount of neighbors. So then we check this thing, right? Which is the first condition, condition 1. Then I suppose we can swap this entire thing. We can swap this entire thing, and this is what we get. We get neighbors again, and we can compare this entire thing to 3. Right, and yeah, so we push this entire thing, and this becomes the second condition. And then we OR them together. I have no idea how you do OR. So there is an ORA. Yeah, so we need to do ORA. So we do ORA, and we end up with this specific condition. Isn't that a Poggers, meine Freunde? What do you guys think? Is that a Poggers line? So here's the thing. When people start working with concatenative languages for the first time, it blows their mind, right? Because you have to sort of like keep track of the state of the stack, and it's really hard. So because of that, don't be ashamed of actually like visually keep track of the stack, maybe on a paper or in the comments like that. It really helps a lot. Don't feel ashamed about that, because I do that all the time, and I'm the author of Porth. Right? It's like similarly to how there's no shame in keeping track of pointers and references when you implement in a linked list. Right? Even the most like prominent computer scientists, when they need to implement linked list, quite often like keep track of the references on a piece of paper because it's goddamn fucking hard, right? So it's totally normal. It's totally normal. Like over time, you kind of develop a mental model where you don't really have to do that anymore. You can kind of like come up with the simple patterns that you can just like reuse over and over again, so you don't have to like keep track of the stacks like anymore. Very funny, very funny. Anyways, so, and for example, I just wrote this piece of code and I don't know if I made any mistake in here. I don't know if I made any mistake in here. So what I want to do, I want to actually double check that. So let's actually go through all of this shit yet again. So I know that at the top of the stack right now we have row and column. I duplicate this entire thing. Okay, cool. Then I do count neighbors, right? So I do n neighbors. Cool. Then I duplicate the neighbors. There we go. I've got duplicated neighbors. Then I push 0, 2 in here. Then I check if they're equal, right? So this is one thing that I've gotten here on the stack. That's cool. Then I swap whatever I have on the stack. So that means I move this thing below this thing. Very cool. Then I push 0, 3 on the stack. So I've got that. I check if they are equal. So I've got that. That is very cool. So, and after that I do aura, and that allows me to combine this thing into a single condition like that. So basically I treat this entire thing as a single element on the stack, right? So, and there you go, I've got a condition on top of the stack. So that's pretty cool. So, and if it's true, right, if it's true, that means here we have to set the new cell, next cell, to alive, right? Because we are alive ourselves, and this entire thing is within 2 and 3, it's 2 or 3, so that means it has to be kept alive. And in fact, I can just right away do this backboard set cell, and I don't have to worry about that. Otherwise, what I have to do, I have to keep it 0, so it has to be 0, 2, jump to R. Boom. Can your C do that? So that's pretty cool. So here is the next cell. So interestingly, yeah, that's actually the computation of the next state of the board, right? So essentially, I just iterate each individual coordinate, and for them, I do next cell. And the next cell does all of this checking of different states and stuff like that, and computes all of that stuff into the backboard. So interestingly here, what we have to do, we have to implement it, right? So we don't know how to set things into the backboard. So first thing we need to do, I suppose we need to get a row and column to be here. I think that's the thing we have to do. And I'm pretty sure that to do that, we have to use the rot opcode. I think that's what we have to do, but I'm not really sure if rot opcode works exactly as that. So let me take a look at like visual representation of the opcodes. So here is the language. Where are opcodes? Where is the rot? So you essentially take this thing and move it at the top. So rot is probably not going to work for us that easily because it basically does that. What if we do another rot? What if we do another rot? I think that should be sufficient. Right, so just let me double check if I understand everything correctly. So essentially we take A, the one that is like below the first two at the top of the stack, and we bring it to the top. So that's basically what it is. We just like bring this thing to the top, and that's basically the rot operation. So the first rot is going to bring that to the top, okay, and second rot is going to bring column to here. There we go. That's pretty cool. So, and essentially we need to convert that into an index or into an NF set within the board. In fact, we already have a code that does that in a board get cell. Let me find that. So here it is. Here is the code that actually performs all of that. But that code, on top of just computing the the offset, it also reads the stuff from the board. So we need to factor out this entire thing, right? We need to factor out. So I think, yeah, I think, so it returns, like, I'm not really sure why do we do swap in here, but maybe that's sufficient enough. So let me actually see what is going on in here. So when we do swap, right, so we just swap this thing around, we push size, we multiply size, and then we add this entire thing. We add this entire thing. Okay, and then, I see. So then we add 0, right, then we add 0. And then we swap it because we need to have like a short that represents the offset. That makes sense. So, and only then we're adding the board, and then reading it. So the whole thing that computes the offset is actually this up until when we push the board, right? So up until that we push the board. How can I do that? So let's call it board offset. So here it accepts the column and it returns the offset. So maybe there is a, how to say that, kind of like a convention that indicates that this is like a U16. I don't know the conventions of this language, so I apologize. I just make up my own conventions. So it is what it is and it isn't what it isn't, right? So this is basically a short, right? So this is basically a short. I kind of like this notation. So that should allow us to do the following thing where we just do, okay, board offset, right? So this is the board offset. So here's the roll column, board offset. Then we take the actual board in here and we're loading it up. Okay, so, and this thing is now more generally useful, right? More generally useful, I think, because now we can use it with the backboard, right? So now we can use it with the backboard. So as you can see, I over abstracted board get cell a little bit. So apparently there was some useful code that could be factored out of that function, right? So, and I fixed that, right? So I fixed that. So let me go here. So we've got that. So now I can do board offset. Then I want to push actually backboard. Right, is it backboard? I think it is backboard, in fact. So here's the backboard, and then I do add 2, and I suppose need to load up. No, I actually don't have to load up anything. I can just do STA. Right, and STA expects the pointer at the top of the stack. STA expects the pointer at the top of the stack. So I think that's the case, but we can always check out. I think that's the whole implementation of this thing. I'm pretty sure. I'm pretty sure that's the whole implementation of this thing. That is very progress. So let me sip my tea. Now, let me see uxn.c. How do you do STA? So STA, yeah. So the top of the stack is T2, so that means it really takes the absolute address, like 2 bytes of the absolute address, and then it takes L, and if I remember correctly, L is the third value, right? So basically we take T2 and then we take the L below it. So that's basically how it works. Right. So, and because of that, it works out kind of naturally. It works out kind of naturally. And funny enough, like we could have maybe accepted them in a right order right away, so we didn't have to do rot. But then we'll still have to do rot in here, right? We still have to do it in here, so we might as well just like do it inside of the function anyway. Right, so let me actually compile everything and see if I didn't make any mistakes. Right, so invalid token board of set. Right, so here's the board of set. Yeah, there we go. So board of set. So there we go. You don't even need reporting of the location in here. You just like, you see incorrect token and you just search through each and individual instance of that incorrect token and you just fix that. Because that was the idea of it, right? So maybe, I don't know. To be fair, the syntax of the whole language is actually simple enough that you don't really need like you don't even have that much of a room for making a syntactical mistake, if you know what I mean, because it's just a sequence of tokens, right? So if any mistakes you will make, they will appear only in runtime, I suppose. Right, they will only appear in the runtime. What's funny is that like we can try to do this entire thing, right? So we can just try to do this entire thing and run it and see if it doesn't have any errors, right? It doesn't produce any errors, so it doesn't segfault, but I mean, I don't know, probably this thing doesn't like never segfaults. Right, so we don't really know if we manage to compute the next state. So we probably have to print the board, right? So we can print the board, but it's not going to help because we are printing the previous state of the board, right? So we're essentially printing the previous state of the board, so it's not particularly helpful. It is not particularly helpful. What we need to do, we need to actually copy the backboard into the main board and then do the print. So that's what we need to do. So let's come up with the operation, I would call it maybe flip board, right? So flip board, it's not accepting anything, it's not returning anything. What it's going to do, it is going to iterate through the board as usual and is going to copy the bytes from backboard into the original board. So that's going to be basically the idea, right? So that's going to be basically the idea. Right, so here we're doing that. So, and here at the top we have basically row and column. So we can quite easily just dupe to them, right? So we dupe to them. So we get that. And then we can do board of set. Man, board of set is actually such a cool function. Right, so yeah, maybe I'm gonna get rid of the board get cell, right? And it's gonna be basically like board of set, and then I'm gonna push the specific board that I wanna read or write or something like that. Right, so here we do board of set, right? So here we have board of set. And essentially, first thing I wanna do, I probably wanna read the backboard. So let me duplicate that specific offset. Right, let me duplicate that specific offset and push the backboard. I'm pushing the backboard. By the way, I should not forget to do increments and updates and stuff like that. To be fair, I think I'm a little bit overcomplicating this entire thing, because when I'm copying one board into another, I don't really care about the shape, about the specific shape of that board. So I might as well just iterate that thing as a continuous buffer, right? So I don't need to iterate over like rows and stuff like that. So let me see. So essentially I have 10, right? So if I multiply 10 by 10, I have that. In hexadecimal it's 64, right? So that's very funny. So essentially here I can do 64, right? So I'm just iterating and I already have the offset. So I already have the offset, right? I usually need nestiness here when I'm printing something or when I'm computing the next state, because I need to look around the neighbors. Though I could still do not nested version and then recover rows and columns from the index. Right, so I could do the division and mod, but mod is a pain in the ass in UXUN, so probably don't want to do that. Don't really want to go into the mod territory. So yeah, so it's better to do nestiness in here when you do care about the shape, but when we don't care about the shape, it's like easier to just like do it like that, I think. Anyways, so we got the offset, and here we probably want to duplicate it, right? So I just duplicated the offset. Then I'm gonna push the backboard, right, back board. So the offset of this thing is rather interesting actually, because it has to be 2 bytes. Right, it has to be 2 bytes, so that means to actually get the proper set, I have to do 0 swap. Right, 0 swap. So I duplicated it, then put a 0, then swapped it around, and this is the proper address. And then I do add to. Right, so board get cell. Right, so let me find it. Board get cell. Yeah. So offset is actually 2 of these things. Yeah, maybe it's fine. So we flip in the board, we add all of that together, so that means we have a you know, plus backboard. And after that we want to do LDA, right? We want to do LDA, so that means this entire thing essentially turns into the value of X. So this is basically the cell. So we've got the cell. Might as well maybe keep this thing like that. Okay, so I got the cell. I need to copy offset from here. I think this is over. I'm pretty sure. If I remember my concatenate, yeah, there we go. So basically over is like dupe, but it copies the thing like over that thing. Yeah. So we do over. So that's the state of the stack we have. We do this thing yet again. So that creates. So there is a very interesting thing. So what is NIP? I remember NIP was something interesting. Removes behind the thing. So maybe I was like, yeah, I just don't remember. Okay, so we've got that thing. Then I do board and I do add 2. So I have a proper offset for the second board, right? So I have a proper offset for the second board, which basically allows me to do that. And effectively, I just end up with this thing, so with offset, and I can just go ahead and increment this entire thing. And so let's call this offset. Right, and yeah. Got cooler. It even looks nice. Look at that. It even looks nice. I really like that. Actually, another interesting thing, we can maintain offset as 2 bytes right away. Which means we can do stuff like that, right, and probably like that. Except maybe, well, in case of not, right, so, well, I mean, when we do this thing, we're gonna end up with a single byte anyway. Hopefully, I'm not actually sure. Are we gonna end up with a single byte? Let me see. So it's not obvious if we're gonna end up with a single byte. Yeah, we're gonna end up with a single byte because T is a single byte, right? So regardless of the mode, whether it's a 1 byte mode, it's 2 byte mode, you're gonna end up with a single byte anyway for LTH. Okay, that's pretty nice. Right, so you do not, so that means here you have offset which is actually 16, right? So that means you don't have to do that, and that makes it even simpler. But here you probably want to do something like this. Right, so that simplifies it quite a bit, which is very cool. Really like that. So yeah, here we compute the next board, right? Then we want to flip the board. And then we want to print the board. So maybe we can even factor out this thing like this. Next board. Let me see. So this is gonna be Emacs next board. I'm gonna put this thing in here, and this one is gonna be GMP to R, and boom, there we go. So here on reset, next board, flip board, print board. We can even first print the board, then compute the next board, then flip the board and print it again. So that means we're gonna print actually two things in here, but I would like to maybe separate them maybe by new lines so they don't fuse together. As far as I know, we have yeah, so we have a break line, so we can do it like that. So it's kind of cool that we developed like a whole vocabulary of actions, and now I can just write my code like this. And it's kind of hard to believe that this is assembly. This is assembly level language, right? So if you come up with the proper vocabulary of things, it's just like, yeah, it's just like actions. But we don't even know if that thing works, right? So we'll see, we'll see. Is it going to work? I have no idea. Let's go. And it didn't work. Epic. It didn't work at all. I'm really happy. So, well, I mean, technically we do have two boards, right? So here is the first board, here is the second board, but it didn't actually compute the state of the next board whatsoever. Okay, so that's very interesting. When I flip the board, so let me double check what is going on. So here, of course. Okay. So I have to do probably dup2. First of all, I probably have to do dup2. All right. Dup2. Then load blah blah blah. So essentially what I do, I end up at the end of this endeavor, I end up with just a cell, which is a single byte, right? So this is basically what I have. So I end up with a single byte. Now I have to, yeah, that's actually a little bit more complex. Like this. It's actually a little bit more complex. How can we do? Can I rotate? But rotate brings the below item. It brings that from maybe. You know what? That thing with a single byte was actually kind of simpler, honestly. I'm gonna go with a single byte. To be fair, I think it was a little bit simpler. So let's go back to simpler times. Let's go back to simpler times, right? Where we just also do swap, right? So we duplicate, then swap this thing, then essentially add 2 and then LDA, and we end up with the cell. Right, so we end up with the cell. So then we do over swap, then add to STA, but then we do increment 1. Right, so I think that's a simpler situation. That's the simpler situation. Let me try to go through all of that one more time. This 0, swap, backboard, and we end up with, let's call it pointer, then we read a cell out of that, right? So that's basically the first thing. We can even put something like that. Right, because as far as now, the brackets are basically ignored, right? So the brackets are basically ignored. Then we do over, offset, we repeat the whole thing, right? So then we do board, then we add it together, then we, right, so we end up with a pointer at the end, and we just store this entire thing, cool, and we end up with something like this. And then we increment the offset, and we just jump around like so, right? So let me actually double check if UXN ASM actually ignores this entire thing. Yeah, I think I looked into that already. Yeah, so I remember looking into that. So if the token starts with one of these things and the length of the token is 1, if it's equal to one of these things, just break out of it, just literally ignore this token. Right, so let me So we don't know if it's going to fix the problem, right? So this is one of the problems that I noticed. So maybe we're gonna have more, right? So, but first, let's just see if it compiles, right? So let's just try to run this entire thing. And we've got something, that's already better. That's already better, look at that, right? So at least it's something new, right? At least it's something new. We can now maybe don't flip the board. What if I don't flip the board? Right, so we print the board. Yeah, no. We don't do the next board. We print the board, we flip the board, which means that whatever we have in the backboard is going to be copied into the front board, and then we print this entire thing, right? So that means in a front board now we have nothing, right? So we know that there's no errors in any of these functions. In fact, I can probably put something in here just in case in a backboard. Let's put like this kind of line, and yeah, that copied perfectly into the front board. So that means in none of those functions, right, that are not commented out, we don't have any errors. So the error is within the next board. The error is somewhere here, which is nice. So we narrowed down the the error. We narrowed down the bug, which is quite important. You know what? I ran out of tea, chat. Chat. I ran out of tea already. The fuck? Actually, I still have a little bit more tea, so just a second. Okay, we can actually go for like a more for 10 minutes now. So, do we have any errors in here? Probably not. Because that's basically the usual iteration over the board, right? So if I compare it with print board, so it's basically the same. So I suppose the error is somewhere within the next cell. In fact, one of the things we can do, we can factor out this entire thing. Like so, and then say, okay, board offset, please compute board offset, maybe even something like this. Always set 1 to the backboard, no matter what it is. Always set 1 and then basically jump to R. Right, so let's just try to do that. So that means no matter what it is within the board, right, it's going to be filled with ones. And that will confirm that there is no at least error in this function. Right, that will confirm at least that, which is good. All right, so okay, that got confirmed. So the error is somewhere here. And honestly, I'm not fucking surprised. To be fair, I'm not fucking surprised that the error is somewhere goddamn here. Because look at that code. Look at it. What the fuck is this shit? Anyways, you got the idea, right? So board get cell, right? So board get cell, I'm pretty sure it works correctly. We already double checked all that, right? Okay. So we duplicate the row and column, and board get cell does in fact consume the whole thing. Right, so board offset consumes that, we consume that, and we get the cell afterwards. So everything seems to be all right. And see any problems with any of that stuff. Honestly, there is some fucky-wucky going on in here, in all fairness. Why we duplicate count neighbors? Next cell is supposed to consume row and column in its well, yeah, that's fine. So row and column is going to be fully consumed by backboard set cell. Right, it's going to be fully consumed by that. That thing does in fact fully consume that. Right, so we do just that, and everything seems to be okie dokie karaoke. All right, so let me think. So if this thing is alive, it is going to jump over. Okay, so then we count the neighbors, then we duplicate this entire thing, we do some stuff, right, and if it's true, What the fuck is 02 in here? Who put 02 in here? Did I put that accidentally there? That's supposed to be 0. What the fuck? Everyone should try implementing the text editor at one point or other. Have you seen my text editor? I'm not sure if it still works, by the way. Let me see. Yeah, it doesn't work anymore, unfortunately. So it doesn't have glue. Can I install glue? Or maybe I have to. Let me try to build and see what kind of stuff I have in here. So we have glue. Yeah, there's no glue in here. Look at that. apt surge glue. Why do I use glue in here? I don't remember. So there's a lib glue dev. Shit. There we go. Drama queen of text editors. Yeah, that is a drama queen of text editors. Yeah, we're almost there. We're almost there. We did it. Can I build it now? Yo, I think I will be able to build it. Look at that. Alright, so let me try to do that. Okay. This is the text editor. This is the text editor. So by default, it supports, I think, C highlighting. So you can just start typing. And that's how it looks like. And as you keep typing. So that's what basically happens. So, as far as I know, there's also, yeah, there's also file manager. Right, so you can open files and stuff like that. So you can navigate here. So there's some shaders and yeah. So there we go. It's a dead text editor. So obviously OpenGL just shits with the errors. I don't really understand why. Right, so if anyone is interested, so here it is. Dead. I don't really actively develop it anymore, but yeah, so it stands for dramatic editor. It's a very dramatic editor, I'm telling you. It's a very dramatic editor. So I didn't use any like a text editor components like Scintilla or whatever it is, right? So it's like literally developed from scratch, and rendering is done with OpenGL. Well, I mean, I used SDL, but I just used SDL as a glorified OpenGL initializer because let's be honest, nobody uses SDL and like differently. Everyone uses SDL as an OpenGL initializer anyway. So yeah. Right, so let me put it in here. So yeah, that's pretty cool. So I wonder if this thing fixes the problem, right? I wonder if that fixes the problem. Maybe it doesn't. So I'm not quite sure. I'm not quite sure. So that yeah, it doesn't fix the problem at all. Doesn't fix the problem at all. All right, so I suppose the time has come to make a small break. Chat. The time has come to make a small break. So, and after the break, we'll try to figure out what the fuck is going on in here. So it is very likely that the problem is somewhere within the function, but I have not figured out what it is yet. So, all right, so let's see what the hell is going on. Right, what the hell is going on? So I'm using next cell correctly, right? So I'm iterating pair of indices, right? I'm duplicating this pair of indices, and then I have next cell that in fact consumes that next cell. So here I'm duplicating this entire thing, and I'm instantly consuming it. So let me actually just go through this entire stuff. Right, so I'm duplicating it, I'm consuming it, getting the cell, right? I'm consuming it, getting the cell, and I already see the problem. Then, or do I already see the problem? I'm not really sure, because there is, yeah, so maybe there is a condition in here, and that thing consumes that cell, so there's no really a problem in here, so that's totally fine. So at this specific point, we don't really have any problems, unless this jump does something weird in here. But anyway, so then I just do that. That consumes the neighbors, then we push this thing, and then we have this condition, which is consumed, and that's totally fine. All right, and then we set 1, and we know that this thing works fine. We know that this thing works fine, and it consumes this thing to its entirety, right? And then we jump back out of that. So that should be fine, I think. That should be fine. So I'm just assuming that this thing consumes the value. I think it consumes the value. I found it's pretty unclear if this thing consumes the element on the stack. So, all right, let me see. I think what it does, it uses GCI, right? So it uses the GCI. And shift, if I'm not mistaken, it basically consumes that. So +1, when you do +1, you actually do -1. So it does in fact consume the value. I think it does. Like that shift indicates that straight up. So, and I'm pretty sure the conditional lambda is basically implemented through GCI. We can look into the assembler to confirm that. So here's the, yeah, so it's straight up GCI. So I think it's like generally used for references and for lambdas as well. So yeah. So it basically has almost no like distinction. It's the same mechanism. It's literally the same mechanism, and it's part similarly. Okay. So then we have that, and in both of the cases we like reach this thing and we jump out of the next cell, unless GCI. So this is literally what I see from the code of the UXN assembler, right? So it's just like if you take a look at the parser, you can see that basically there is a distinction between whether it's a ampersand or the curly brace, right? But the idea, the mechanism is sort of like the same. The mechanism is sort of the same. All right, so this part, I don't see any problems with this part, honestly. I don't really see any problems with this part. So then, if this thing is like true, let me go through this entire stuff one more time. We do dupe2, we count the neighbors. All right, we duplicate it, then do 0, 2, check if it's equal, swap around this thing, 0, 3, check if it's equal, right, then do aura. Right, so then we do aura, and do the following thing. So if this is true, we right away just set 1 to that. We just right away set 1 to that. So far so good. So far so good. Like I don't see any errors in here anywhere. So maybe there's something with the count neighbors, but we double check count neighbors before, didn't we? I think we double checked the count neighbors before. We can try to double check count neighbors one more time. So let's go here. I'm going to comment out all of these things and essentially 0, 1, 0, 1 count neighbors, and I think we have print text. Yeah, we have things like print hello world n times, right, which allows us to basically test. So we can even try to do the following thing. Just do that, and hello world was printed 1 time, so 2 times, 5 times, boom, everything seems to be fine. So then we can do count neighbors, right? We can do count neighbors, and all right, so we found an error. Count neighbors is broken. That's really funny because we literally check it recently? Didn't we literally check it? Yeah, we checked it on the previous stream. So count neighbors is broken. Who broke count neighbors? Chat, who broke count neighbors? They worked before. What the fuck? So that's kind of It's kind of weird. So yeah, so now it is 1, but if I put 0, 0 in here, right, if I put 0, 0 like here, there should be 5 of them. There should be literally 5 of them. Okay, so what if I put like 0, 0 like that? Yeah, there's literally no neighbors in here whatsoever. So count neighbors is broken. We found the error. Damn, okay. So let me see. Where is the count neighbor implementation? So we move 0 into the second stack. So can I just do pop2 in here? Pop2. And just return 6. Right, 0, 6. So pop2, 0, 6. That seems to be working. So that is in fact correct. All right, so we're moving that. So then I duplicate rows and columns. Then I move things to the left, right? So I move the whole thing to the left, and then board get cell. But I know that board get cell works correctly, doesn't it? Right, I know that for a fact. So I can double check it, of course, right? So board get cell, I can get the cell at, for instance, 0, 0, and then I can print this thing, and it has to be 0. And if I get, for instance, column 1, right, if I get the column 1, it has to be 1. So everything works correctly. Board get cell is in fact correct. Let me see, where is the implementation? So we do board offset on this entire thing, then we add this thing together. When loading up, everything's fine. Okay, count neighbors. So something may be wrong with this thing, like left. I remember like messing with them a little bit. I do kind of remember. So maybe this is because of the overflows and stuff. That could be because of the overflows. Yeah, okay. You know what? We may try to get rid of the overflows. Right, so left is just decrement. Left is just decrement. And right is simply increment. Right. We got rid of the overflows. I think the overflow broke it. It might have been actually overflow. Right. So overflow broke it. So up is that, we swap it around. Okay, so that's totally fine. So now if I try to get the amount of neighbors at 1, 1, right, if I try to get the amount, it is 0 because I commented out. Okay, that's fine. Chat, that's fine. Count neighbors, that's fine. So I want to make sure that the problem is with overflow. Overflow broke it. We added overflow. We were really proud on the previous stream. We pat ourselves on the back, but shit didn't fucking work. Damn! All right, okay. Yeah, and if I do overflow, it just does that. Let me see. So what exactly is going on? What exactly is going on? So I have a column, right? If it is positive, I just skip this entire thing and simply decrement it. Makes sense to me? Makes sense to me. I don't see any problem with that. That's kind of bizarre. So if it is equal to 0, so it's going to underflow. So that means we pop that thing and we replace it with a size and we decrement the size instead, which is precisely what we want. I don't see any problems in here whatsoever. Honestly, I don't see any problems in here whatsoever. So I think the underflow in here is correct. So, all right, let's take a look at this thing. We do increment. And if after incrementing this thing becomes equal to the size, we go into here and we replace it with 0. That seems fine as well. This one's kind of weird, honestly. Right. We incremented it. It's not equal to the size. We just leave it as it is. One character. Okay. Didn't work. Failed to assemble ROM. Just a second. Okay. So let me follow the stack. All right. Let me follow the stack. So I have column. Then I put the size. And I suppose I can just do dupe 2 on this stuff, right? No, not really. What I want to do, I want to duplicate the column after I incremented this entire thing. Then push the size, I push the size. Then I want to do not equal on this entire thing, not equal to this entire thing. And of course, let's remove the key. And then I do the checking, right? And I do the checking, and that thing, in fact, consumes it. I think that's what needs to be done. That's what needs to be done. That's what needs to be done. Exactly 5. Exactly 5 of them. My God. We can even double check how that stuff is going to work. So there's only 1. Is that correct, meine Freunde? Okay, so that is in fact correct. So because if you look around, there's only 1 neighbor. Now, what if I put 1 in here? There should be 2. There's 2 of them. Chat, there's 2 of them. It actually wrapped around. Okay, so we're Gucci. We are in fact Tamaguchi. Okay, so I'm gonna print the board. Cool. I'm gonna compute the next board. The next board is computed. Everything is correct. We're gonna flip the board. We're gonna break the line, and we're gonna print the next board. Okay, so I'm pretty sure where we had so did we had some testing code somewhere where we just set next cell to every... No, that could not be true. That could not be true. Damn. All right. Wait a second. Let me just not do next board. Okay, next board is fine. So next board does not contain like anything in here, right? So this is just that. Flipped too much. Yeah, I think I flipped too much. But if I do the next board, that is actually worse than it was before. What the fuck? All right. So, but flipping the board works, right? Flipping the board works, which is fine. All right, so there's still problem with the next board. All right, there's still problem with the next board. The next cell. Right. So now let me take this entire stuff. So I'm gonna set maybe 01 backboard set cell. Aha. So there is some incorrect stuff in the backboard set cell. which is, excuse me, what the fuck? Right. So if I do next, well, I mean, I forgot to do this thing, of course. Yeah, okay. So that's everything. Everything seems to be fine. Now it's that. Maybe I just have to flip some of these things. Maybe I just have to flip some of these things. Let's go through that stuff one more time, okay? So let me take a look at the definition convoy of game of life. So if the dead cell exactly 3, it becomes alive. If a live cell has fewer than 2, it dies. It has more than 3, it dies. So it basically stays alive even when it's 2, 3. Okay, so that makes sense. That makes sense. So we get the board cell, If it is false, that means it is dead. If it is equal to 3 exactly, we set the backboard to 1 and jump out of that. Otherwise, we set it to 0. That makes sense. Everything's fine. So after that, we count the neighbors, right? So this one is okay. This one is okay, but so it's only something with the next board. So let me do the following. Board get cell. So we do 0, 0. Print. Print. What's that? Print hello world. Print hello world. Print hello world. So that should be 0. 1, 1 is 0. 0, 1 is okay. Count neighbors. I want to double check that. I'm sorry that I want to double check that one more time. The mode is kind of weird. Who wrote the tokenization for this mode? Honestly, count neighbors. It's 1, but 1, 1 has to be 5. All of these things are correct, and I know that for a fact. So all of these things are correct, and I know them for a fact. So then I just duplicate that. That is fine. Then next cell. Yeah, so there must be problem somewhere in this logic. Backboard set cell, I really don't see. So row cell, right? So row column cell. So we rotate a couple of times. Then we compute the offset. Offset actually returns the short. We know that also for a fact. Then we add them together. Then we load. We store, right? So we have a pointer, right, like this, and which is U16, and we store it. Everything is fine in here. Everything is totally fine in here. So there must be problem with the logic in here somewhere. There must be a problem with the logic in here somewhere. So we get the cell. If it's alive, we duplicate this thing, we look at the neighbors. Let me double check this thing. Row column, duplicate, neighbors, duplicate them, 0, 2, equal, swap 3 equal. I can't even read this entire thing, so I don't see any problems in here. And if it is true, we must set the backboard to 1. So that is correct. Otherwise, we set it to 0. This entire thing is correct. I don't see any error. So if it is false, we compute the neighbors. Is it equal to 3? So if we're dead and equal to 3, we set it to 1, jump out of it. Right. So, and otherwise we set to 0. I literally don't see any problem in this logic. One of the things we can do. So one of the things we can do is, can I just basically maybe take dupe to board get cell not backboard set cell jump to R. So essentially we're gonna invert the current board. We're gonna invert the current board. So that way I'm gonna, yeah, that is correct. That is correct. So everything is correct. So I do not understand, I might be not understanding something about this shit. So something is wrong in here with, I don't know, man, maybe with labels. So we can do the following thing. We can say alive, and this is gonna be alive, like so. So yeah, so you do that, you become alive, right? So, and that's basically like the logic for alive. So here, if you equal exactly to 3, we can say born, like so. You get born. So, and in here you basically stay alive. Here you basically stay alive. Stay alive. Stay alive. So I double checked literally everything in here. So all of these functions that we use here work correctly. All of these functions work correctly. So that means I don't understand something about the lambdas. Don't understand something about the lambdas. Yeah, so that didn't change anything. So what is incorrect in here? What is incorrect in here? So that's really bizarre. That's really bizarre. I keep bisecting this entire thing, and everything basically brings me back to here. Like everything literally brings me back to here. So even the fact that if I simply just invert whatever we have in here, just simply invert whatever we have in here to just not backboard set cell, and then jump to R. So yeah, so it just basically reverses this entire thing. So that means everything works correctly. Everything, literally everything works correctly except that piece of code. Why that exact piece of code doesn't work correctly is kind of beyond me. And it's not about lambdas doing something unexpected on the stack because I replaced them with just labels. I replaced them with just labels, and that didn't change anything. So that means there is a problem with the logic in here. There is some sort of a problem in logic in here. And I wonder if something on the edges of this entire thing. What if I do the following thing? What if I kind of change this entire stuff like so? Right, so what if I move this thing away? And it literally inverts the, but why does it invert the code? Like, I don't understand. So that means I just misunderstand the lambdas. Lambdas are extremely confusing, honestly. They are extremely confusing. So do what if I literally invert these two things? And I don't think, it's just so bizarre that, okay, but that is not the next state of the glider. So that's the problem. I don't think it is the next state of the glider, because if we try to go to the next iteration, if we try to go to the next, yeah, this is not the next of the glider. It's just like not correct whatsoever. So no, that kind of works in an interesting way, right? That kind of works in an interesting way, right? And then that definitely should not disappear, by the way. That definitely should not disappear. So, what is wrong with lambdas? They're so confusing. But maybe, okay, so the problem is not lambdas. Again, I replaced them with labels and they worked fine. There's something else somewhere. There's something else somewhere. When I count the neighbors, by the way, speaking of the count the neighbors, I'm messing with the return stack. I'm messing with the return stack, so that means, but I'm actually restoring everything from the stack, so that should be fine. Right, so I'm actually restoring everything from the stack, so right, I'm accumulating all of these things and just like go back, and that's fine. That's fine, that's fine. Interestingly, so maybe I had to reverse only one thing in here. So I don't really like that I'm now trying to guess things. This is really bad. This is really bad. So when you're guessing things, that means that you... Okay, why this shed is opposite? This is correct. This is correct. Why this shed is opposite? Right, so it should not be opposite. If so, this thing is true, this thing is true, so we're jumping over it, we're duplicating it. This has to be AND. This has to be AND. This has to be AND for that shit to work. I got it. It's not aura. Do I have ANDA? But why is it not called ANDA? It has to be called ANDA, I'm telling you. ANDA. And sorry. I figured it out without a debugger. Okay, so let's actually see if it works or not. Right, so no, it's actually OR. It has to be, wait. It has to be OR. So if this thing 2 or 3, they were the confusing lambdas. They were the confusing lambdas. They were the confusing, but I figured it out without the debugger. I figured it out without the debugger. I figured it out without the debugger. I'm still holding a strong opinions that lambdas are confusing. They are confusing. I'm sorry. They are confusing. It's just like, it's like, I'm sorry. You can say whatever you want. You can even threaten me with the skill issue, but it's confusing. It's just like, it is confusing. I've been programming for 20 years. It's confusing. Sorry. Because it feels like an opposite if statement, because it feels like unless. Though there's honestly nothing wrong with unless. You know, so in Lisp, there is this thing. Unless. Right. So it's like not thing. So yeah. Figured it out. We figured it out. That's actually very much poggers, meine Freunde. That's very much poggers. Okay, so yeah, now we can actually keep repeating this entire thing. Right, we can keep repeating it several times, as many times as where is the... Yeah, and now this thing is moving. This thing is moving. I can actually do that in a loop. So let's actually do the following thing. I'm going to put the iterator here. So then I'm duplicating the iterator. Then I'm say, okay, let's do that for 3 iterations, right? So it's a less than, and if it's not, right, if it's not, we're gonna keep doing that. Yeah, boy. And then we just increment this entire thing. And then we pop. All right, so that's... They're kind of useful for loops, right? For loops like this, that's for sure. Well, no. I don't think that's what I wanted to do. Yeah. So what I wanted to do, actually... Again, I wonder if we can. Well, probably not, but I mean, yeah. Yeah, look at that. I'm going to start calling this weird loop a syntax at Sodium. Really, this is not how you do loops. This is not how we do loops. Let me actually see how we do loops. Let me take a look at the projects. So there's some demos. Bunny mark. Okay. So I suppose it's just. Honestly, there's not that much of a structure to it. So you. It's just a regular. So here is the regular loop in here. Factal. Okay, just a second. That doesn't exist. Example. Oh, it's Phoebs. Okay. Wait, am I missing something? Project examples. Oh my god. All right. So. Okay. Just a regular jumping around, nothing particularly special. I see. Anyways, so we got this thing, but that's not enough, right? So what I want you to do, I want you to actually maybe do some graphics, right? So we want you to display all of that on the screen, but how much time it will take to do so? How much time it will take to do so? That's a very good question. So maybe we could actually. So we already know how to do the sprites, right? So we know how to do the sprites. So essentially, we know that sprites are 8 by 8. We could predefine sprites. Essentially, something like a live sprite. So maybe something like, and it's going to be like FF 8 times, right? FF 8 times. Just a second. All right, so this is a live one. Can I do something like this? And this is going to be the dead one. And so here I'm just replacing F with 0. Boom. Right, and just like we're going to be drawing these sprites at corresponding places and stuff like that. And that should be enough. That should be enough. So the only thing we have to do, honestly, is just prepare the screen. We need to prepare the screen. And on the callback on screen, and the callbacks are called vectors in UXN, we compute the next board. And the only thing we need to write some code that iterates through the board, right? It iterates through the board, and depending on the state of the cell, it just renders different sprites at the corresponding places. So that's what we need to do. That's what we need to do. So let's see what we can do in there. All right, so I'm gonna remove all of that. We don't need all of that stuff anymore. Let me go to the code where I did the, the heart thingy, right? So where I did the heart thingy. So I think it was graphics style. Yeah. So let's go there. So UXN graphics ROM, and so it's actually UXN emu. Yeah, there we go. So here's the heart. It is moving down, right? So, and we can use a similar trick to sort of do the graphics, right? We can do a similar trick to do the graphics. So now I'm gonna go back to the goal tile, And on reset, so we have the notion of a set theme. I'm not sure how useful it is for me, but I'm gonna just like copy paste. Like when I don't understand a particular code, I just copy paste it. So in here, I also go into set the theme, and we need system. We need a system, and we need a screen. We need a screen. System and a screen, and then what we're doing, we're just setting up the vector. We're just setting up the vector, and our vector is going to be on screen, like so. So this is a vector, right? So that's pretty straightforward. So it's 60 FPS, right? So that means we probably need to have a way to maybe skip some of the frames because it's going to be too fast if you think about it, right? So it's definitely going to be too fast, but maybe that's fine. Okay. So we need to compute the next board. We compute in the next board. Then we flip in the board. And then we already have a print board, but we need to have another one, display board. And then we'll be okay out of this thing. So that's basically how we transition from the console to actual like a graphical display stuff. So the only thing we need to do, we need to implement the display board, and also maybe skipping the frames and stuff like that. So let's actually go to print board, and we can do this thing in a similar fashion, right? So like this. So jump to R. And in here, we don't need to break the line. We don't need to do any of this stuff and everything. So now we need to get the board. So this one is really interesting. This one is really interesting because we probably want to have a separate function for that. So here we have row, column, and cell, right? We have a row, column, and cell. Maybe we could have a function, something like display cell. Display cell accepts row, column, and cell. Does nothing. And just basically displays the corresponding sprite depending on like what we have in here. So honestly, it is actually super easy to do it like that, I think. So we can treat the cell as a boolean. So if how can we even do that? That's a good question. Maybe I can, yeah. Because I know that in here, when you're about to render something, so there's a ADD, yeah, there we go. So what I'm thinking is that if we had a function, something like cell to sprite, so this thing accepts the cell and returns the address of the sprite. So it should be relatively straightforward. If it is true, right, if it is true, we return sprite alive, right, we return sprite alive, and then GMP to R. If it's false, we return sprite dead, and also GMP to R. So that's basically what we have in here. So we have cell, we convert that cell to a sprite, and then we send that sprite to screen address. So the only thing that is left in here, actually, so the only thing that is left in here is to find, you know, X and Y, the corresponding X and Y. To be fair, column is already X. Column is already X. So the only thing we have to do, we have to multiply it by 8, right? Multiply it by 8. And this is the position. It's actually, yeah, so it's not what I want, but whatever. So we multiply it by 8. We'll make it over. It's probably never gonna overflow, honestly, because we have 10 by 10, and so we're gonna have 80 by 80. So the whole thing is gonna be 80 by 80. We don't have to worry about it. So we're gonna do 0 SVP. So that turns it into what is it called? Into short that we can basically save into X. Then we only have row. Multiply, we turn it into short 0 screen y DO2, and there we go. So we got cell, row, and column, and we translated all of that to sprite, then to the screen coordinates. Sprite and screen coordinates. In fact, we could probably factor out this thing to something like coord to screen. How, let's put it this way, maybe board to screen. Right, so you accept like a board coordinate, a single board coordinate, and you get a screen coordinate or something. I'm not sure if it makes any sense, but that way you can actually write something like this, board to screen. So that's actually kind of cool, isn't it? I think it is. I think it is. And the screen is supposed to be like a 2 bytes and stuff like that. Right, so then you just display this entire thing. But we never specified the size of the screen. And what's interesting is that I don't remember how to do that. So there should be something like, you probably set screen. So let me find the devices, the description of the devices. Oof. I would expect maybe it's memory. Honestly, I would expect to get the reference of the devices in a thing called UXCN devices, but I didn't get that. I think it's because it's a var. Okay, so I see. UXCN is just a virtual machine. Var is the system that includes the devices. That's probably the case. Yeah, okay, so that's the thing that includes the devices. Okay. So, okay, you have width and height, and ports can be set to resize the screen for the system that's supported. That makes sense. Okay, so that is bizarre. So what is SFT2? I don't remember what is SFT2. So let me take a look at the UXCN like UXCN.c SFT. Some sort of a shift stuff. Right, so you have top and thing below the top. Okay, so yeah, what? Shift 2. Maybe it doesn't really matter, honestly. Maybe it doesn't matter. But that's such a bizarre explanation. Reading from this port always return the actual size. I suppose what I have to do is to just maybe set why we are reading in here. This is such a bizarre example. Right, I would expect an example that just sets and like shows how to set it. Like why is it so complicated for what it... Okay, so we said that screen width, and I suppose I wanna just do 80 multiplied by 10, so, and we can take a look at the hex. So it's 50. Okay, so this is gonna be 50, and I suppose I just do DEO, but maybe I do DEO. Can I just do DEO 1, or do I have to do DEO 2? Where is the width? Where is the width? Maybe I can we can take a look at the width in here. Width is actually 2. Width is actually 2, which probably means that I have to do something like this. Right. So it's going to be height, and of course it's a DEO 2. Let me take a look at... Yeah. So, because like you definitely want to have width that is bigger to 156, that's for sure, right? So that's why it's 2 bytes. You set the width and stuff like that. So to double check everything, let me just compile this entire stuff and see if it works. So invalid label dead alive. Really? So you have to put a new line in here? Is that what you're telling me? Or, oh, no, probably not. Probably alive. No. So do I have to put a new line in here? I want to put a new line in here. No, it's not the case though. But I don't know where exactly the problem is. And dead. And because of that. Invalid label dead in alive. What? Excuse me? So just a second. Dead is a hex value. I need more tea. I need more tea. The plot thickens. The plot thickens. I can't even call a label coffee, babe. I could. Okay. So it compiles. Okay, that's cool. Now, so yeah, so everything seems to be okay. And if I try to run, okay, so this is CLI. I should use actually emo. But I mean, if it's a good start, it's a good start, okay? It's a good start. Now, what we're gonna do in here, I want to probably display the, like, whatever we have already. So I want to display. So is it really correct in here? Is it really? I think it is, isn't it? So Python 15. Okay, so it's 80. You have 8 by 8, right? Because it is 8 by 8, right? It must be 8 by 8. Yeah. Oh boy. Is it possible to actually make a bigger sprites? I feel like... so what's up with sprites? Sprite. Pixel port defines the pixel or fill mode layout. Yeah, there's some really complicated stuff in here. Defines a 1-bit or 2-bit mode layer to draw on optional horizontal and vertical flipping of the sprite cause the 8x8 sprite data to draw specified by writing its location to okay, so they're all 8x8 kind of, right? So they're all 8x8. By the way, I think I can actually it's kind of funny that I keep adding like opening Python consoles and forgetting about them. I need to actually garbage collect them from time to time. All right, so let me try to do that, and it's an emulator. How do I scale it up? Oh, I can just, yeah, I can do shit like that. Yeah, boy. Okay. So now, where is on screen? I want to go ahead and just display the board. That's what I want to do. I want to just go ahead and display the board and see how it's going to display it. How it's going to get displayed. Honestly, I can just do something like this. I can always do something like this where yeah, it's not that big of a deal. I can always dupe 2, get cell, convert cell to sprite, set it to the address. So yeah, I think that's even better. Right, so let's go. Can't see shit in this mist. Fuck. Can't see shit in this mist. Okay, that didn't work. I'm disappointed. I'm actually disappointed. All right. So we have coordinates there, then we multiply it by 8. I think that's correct. Then swap, and that's what we have in here. Aha! Well, I mean, so we do actually include like a, you know, it's 16. All right. So on. So, oh, I remember there was also, you have to do the call to the sprite. Yeah. You have to do the call to the sprite on screen, display the board, display the cell. So you also have to do this thing, that's for sure. Boom. Are you seeing what I'm seeing? First try! Dab. So we need to skip some frames, I think. That's so fucking funny, I love it. That's so freaking funny. We did it. We did it without using any debugger. Debugger wagger. So how can I skip the frames though? So we need to allocate some sort of a like a frame skipper, I suppose. So I don't know, like a count, and it's gonna be like literally a single byte. Let's call it frame count. It's called frame count. And then here on screen, on maybe yeah. So let me see on screen. On screen. There we go. So we take the count, right? So this is the frame count, and of course you want to do something like that. Of course, you LDA this thing. So you read 1 byte. You literally read 1 byte. Sure. Then you want to increment that. And you want to kind of store it back. So STA, sure. On top of that, we can read it again. And if it is equal to 0, right? If it's equal to 0, right, we're gonna let it through. We're gonna let it go through and do the thing. Otherwise, we're gonna break out of that. We're gonna literally skip. So essentially, yeah, it's gonna go 256. So for every 4 seconds, it's gonna compute the next state. So it's kind of too slow. That didn't work. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. Anyway, so one of the things we can do. Okay, we can say that it is how many frames. The frame count is greater than 10. It's greater than 10. The frame count is greater than 10 we want to actually skip and start doing this thing. And if it's greater than 10, we kind of want to actually reset it to 0. We want to reset it to 0, like so. If it's less than 10, we're keep incrementing it. So that's how we can kind of control that. Right, so we have a count, we're loading it up, it's greater than 10, okay, we're resetting it to 0, we're doing this stuff, okay. If it's less, we keep incrementing it, but we keep kind of skipping from that stuff. There we go. And now we can even control the speed, so I can say, okay, 5 frames, so that should be a little bit faster, so that's a little bit better. So yeah, that's my first more or less substantial program in UXN. I still have no idea what the fuck it is. This is really confusing. I'll probably never master it, but I implemented a very simple game of life. We can maybe add more interesting stuff in here. So let me actually put the gliders somewhere here. So this is going to be another glider. In fact, we can keep piling, yeah, so we can keep piling gliders here. So yeah, that's pretty cool. Yeah. Let me maybe, can I, maybe I can place them somewhere here. So this is going to be another one like here. 0, 1, 1, 0, 0, 0. So, and in here we're gonna place probably another one. So I want them to march, if you know what I mean, right? So I want them to march. I hope they're not gonna collide too much. Oh, okay, so they collided too much. I mean, that's fine. At least we tested how the game of life actually works. So yeah, make it bigger. So making it bigger kind of means that I have to like restructure literally everything, right? So because like the size is literally hard-coded in here. Right. So the final thing is gonna be like this. Right, so I think this is gonna be basically the final thing. So let me see. Can I release it under MIT? Right, so where's the, so how do I do MIT? I don't remember. Yeah, there we go. So this is MIT, and can I put that behind the copyright? Is that a good copyright? And I suppose I'm going to just upload it to GitHub for anyone who's interested. So I'm going to put it on the gist. MIT opcode to indicate oh, it's I just read it and thought that it's actually like legit true. I didn't think there is such opcode. Yeah, well, that would be funny, honestly. That would be funny. Right. Maybe I should actually upload it on the public domain. To be fair, I uploaded one patch on the public domain once. Somebody took it, made an entire project around it, and got viral on Twitter. So I don't know, man. I don't know. So I'm probably not gonna do that stuff anymore. Create a public gist. Yeah, there we go. Here's the first program in UXN by Zozin, if anyone is interested. Feel free to extend it, feel free to do whatever you want with it, you know, within the MIT license and stuff like that. And for people who's watching on YouTube, I'm gonna put it in the description. If I ever going to upload it to YouTube, I'm not sure if I will, because the final VOD is gonna be pretty huge. I think it's gonna be around 4 hours, right? So I Didn't expect that it's going to take 4 hours, but I was learning this entire system on the fly, honestly. I didn't prepare. I tried to prepare for this thing, but the documentation, I couldn't read documentation, honestly. Like, I couldn't understand documentation, but then I looked into the source code and realized that, okay, I can quickly look up like very specific details about the implementation in the source code. The source code is readable, and I just jumped into implementation, and here's the result. It took me 4 hours, actually 5 hours, to implement it. Right, so, but now, yeah. So is it good? You can probably implement it way simpler if you put more thoughts into that and learn the entire system a little bit better. I'm pretty sure a lot of things I did here are really weird, cumbersome, and stuff like that, but that's just my first attempt at this entire thing. Did I do well? Did it well? Okay, the creators say that it's good. Okay, thank you so much. But the creators also trolled me with -1 with this thing, so I'm kind of hesitant to trust them. So anyway, I guess that's it for today. So we got some subs, by the way. We got some subs. Core Runner, thank you so much for tier 1 with the message. Modern JavaScript, I'm more of a postmodern JavaScript user myself. I don't use JavaScript. I have no idea where you see JavaScript on the screen, but thank you so much for gifting money to Jeffrey Bezos. That's it for today. Thanks everyone who's watching right now. I really appreciate that. Have a good one, and I see you all on the next recreation programming session with Mr. Azuzin. I love you. Mwah.